We live our lives by an unspoken rule. The past is fixed, and the future is open. Causes happen, then effects follow. It's a sequence that feels as fundamental as breathing. An arrow of time that flies in one direction, from yesterday, through today, and into tomorrow. But in the deepest parts of reality, and at the most extreme edges of the cosmos, something strange happens. It appears that this arrow can bend. That it might even, in some way, turn back on itself. The universe, it turns out, operates on rules far stranger than our common sense suggests. And the logic that holds our experience of reality together seems to be more of a suggestion than a law. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. We are going to explore the precise points where that logic begins to dissolve. It's a journey that will take us from our familiar world, down into the bizarre realm of quantum particles, and then out to the edge of a black hole. We assume that cause always comes before effect. It's the invisible architecture that separates memories from possibilities. But modern physics has found places where this architecture seems to warp. Places where an effect can appear to happen before its cause, where a decision made in the future seems to leave its trace on an event that has already passed. So the question is not if causality breaks down, but where. Where is the line where the universe stops making sense in the way we expect it to? The unbreakable rule we live by. Before we explore where a rule breaks, we have to understand why it feels so powerful in the first place. Causality seems simple. A causes B. The lightning flashes, then the thunder rumbles. This relationship, where a cause always precedes its effect, is what creates the distinction between the past and the future. The past is the realm of causes that have already happened. The future is the realm of effects yet to come. Without this ordering, time itself would become a collection of disconnected moments. But how do we know, really, that one thing causes another? The world is full of correlations. A rooster's crow is followed by the sunrise, but we know one doesn't cause the other. This is where science offers a more powerful, and slightly strange, way of thinking: the counterfactual. The idea is this. A causes B if, in a world where A didn't happen, B would not have happened either. It's an act of imagination. When we say an aspirin cured a headache, we are making a claim not just about our world, but about an imagined, parallel world where the aspirin wasn't taken, and the headache remained. This is the hidden logic we use every day. It's how medicine is tested, by comparing a group that gets a drug to a control group that doesn't, creating a real-world counterfactual. It separates true causes from coincidences. In a world where the rooster was silent, the sun would rise anyway. But in a world where you didn't flip the light switch, the room would have remained dark. Sometimes, a cause is necessary. You can't have fire without oxygen. Other times, a cause is sufficient. Striking a match is enough to start a fire, but so is using a lighter. They are different sufficient causes for the same effect. Most often, events arise from a web of these causes. This is our starting point, a stable, predictable world, governed by what feels like an unbreakable law. It's the scaffolding that holds our reality together. But as we move further from our everyday experience, we will begin to find that this scaffolding starts to creak. And in the strangest corners of the universe, it seems to disappear entirely. The first cracks, where causality gets weird. For most of our lives, the simple A causes B model works. But you don't have to travel to a black hole to find where this tidy picture gets complicated. The first cracks appear in systems of immense complexity, right here on Earth. Think about the weather. What is the single cause of a hurricane? Is it a patch of warm ocean water? A pressure system? The Coriolis effect? The answer is all of them, and none of them individually. A hurricane is an emergent phenomenon, born from a dance of countless interacting variables. You can't point to one sufficient cause. The idea of tracing a clear line from A to B dissolves. If you tried to imagine a counterfactual, in a world where A didn't happen, you wouldn't even know what A is. The system is so interconnected that the idea of a singular cause becomes less meaningful. The same is true for a stock market crash. Is it caused by a bad report, a political event, or a wave of panic? It's a cascade, a feedback loop. Bad news causes selling, which causes prices to drop, creating more bad news and more selling. Here, the effect, falling prices, becomes a cause of its own continuation. This is known as circular causality. Consider a simpler, human example. A person is lonely because they are shy, which prevents them from meeting people. But they are also shy because they are lonely, which has eroded their confidence. So, which is the cause and which is the effect? In reality, it's a self-reinforcing cycle. Each element is both a cause and an effect of the other. The arrow of causality isn't a straight line, it's a circle. These complex systems don't break causality in a fundamental way. The laws of physics are still operating on individual molecules and trades. But what they do is suggest that our simple, intuitive model is just that, a simplification. It's a tool that works well for simple systems but starts to fail when faced with the messy, interconnected nature of reality. This is the first clue. The breakdown of causality isn't always a dramatic event. Sometimes, it's a slow blurring, where so many causes and effects are woven together that trying to untangle them is no longer possible. This prepares us for a much deeper truth. Because as we shrink down to the quantum world, we find that the arrow of time isn't just tangled. It can appear to point in the wrong direction entirely. The quantum leap, causality shattered. If complex systems show us cracks in causality, the quantum realm reveals something else entirely. Here, the rules of our intuition don't just bend, they seem to operate on a different logic. This is where we find the strange possibility of retrocausality, the idea that an effect can, in a way, precede its cause. It begins with a concept called quantum superposition. In our world, an object is in one place at one time. But in the quantum world, before it's measured, a particle like an electron exists in a superposition of all its possible positions at once. It's not in place A or place B. It's in a probabilistic cloud of A** and B. This alone makes our counterfactual definition of cause and effect difficult. How can we say, if it didn't happen, when the state of A is that it both happened and didn't happen at the same time? But the story becomes truly unfamiliar with one of the most baffling experiments in physics, the delayed choice quantum eraser. The full setup is complex, but the idea is what matters. Imagine firing a single photon at a double-slit barrier. If we don't watch which slit it goes through, it acts like a wave, passes through both, and creates an interference pattern. If we do watch, it acts like a particle, goes through one slit, and the pattern vanishes. Now for the twists. After the photon passes the slits, a special crystal splits it into two entangled twins, a signal photon and an idler photon. The signal photon heads to a detector, D0. The idler photon is sent on a much longer path to a different set of detectors. The delayed choice comes from the fact that the signal photon arrives and makes its mark at D0 long before we do anything with its idler twin. Now, we play a game with the idler photon, well after its sibling's journey is over. We randomly choose to either measure it in a way that reveals which slit its twin went through, or we send it to a quantum eraser that scrambles this information. Here is the strange result. When we later look at the data from D0, we sort the signal photons based on what we later chose to do with their twins. The signal photons whose twins had their path information measured show a simple, particle-like pattern. But the signal photons whose twins had their path information erased show a clear, wave-like interference pattern. Let that sink in. The pattern a photon created in the past seems to depend on a choice we made in the future. It's as if the signal photons knew what we were going to decide and adjusted their behavior. This looks, for all the world, like retrocausality. Now, physicists are quick to point out that this can't be used to send a message to the past. The strange patterns only emerge after we correlate all the data, which can only happen after everything is finished. Still, the philosophical weirdness remains. The phenomenon that allows for this is quantum entanglement, what Einstein called spooky action at a distance. When two particles are entangled, their fates are linked. Measuring a property of one instantly tells you the property of the other, no matter the distance. While you can't use this to send a deliberate message faster than light, because the individual measurements are random, the correlation itself is instantaneous. It isn't caused by a signal traveling from A to B, it just is. It is a property of the system as a whole, existing outside our normal concepts of space, time, and cause. The quantum world suggests that cause and effect may not be fundamental. They might be emergent properties of our large-scale world, while at the bottom, reality operates on a different logic of correlation and entanglement. The edge of everything, black holes and time. Having seen causality blur in the quantum realm, we now journey to the other extreme, the cosmic scale, and to black holes. Here, it is not quantum uncertainty that changes the rules, but the immense force of gravity, as described by Einstein's theory of general relativity. General relativity revealed that massive objects don't just pull on things, they warp the fabric of spacetime itself. A consequence of this is time dilation. The stronger the gravity, the slower time flows. This is a physical reality. GPS satellites have to adjust their clocks because time for them runs slightly faster than for us on the surface. A black hole is the ultimate expression of this. It is an object so dense that it creates a boundary, an event horizon, from which nothing can escape. To a distant observer, someone falling toward a black hole would appear to slow down, eventually seeming to freeze at the edge for eternity. From the perspective of the person falling, however, time would feel normal. They would cross the event horizon, but in doing so, they would cross a causal boundary. Inside, the warping of spacetime is so severe that all possible paths lead to one place, the central singularity. The future is no longer a direction, it is a destination. But where does causality truly break? It breaks in the theoretical possibilities that emerge from the mathematics. Some solutions to Einstein's equations permit closed time-like curves, CTCs, paths through spacetime that loop back to their own past. This brings us to the grandfather paradox. If you could follow a CTC, travel to the past, and prevent your grandfather from meeting your grandmother, you would never be born. But if you were never born, you couldn't have gone back in time in the first place. The effect eliminates its own cause. Causality devours itself. So how does the universe deal with this? One idea is the *Novikov's self-consistency principle. It suggests that any event that would create a paradox has a probability of 0. The universe simply won't let you do it. If you went back to change the past, some improbable event would always intervene. You can be a part of the past, but you cannot change it. Your presence is already factored into the history that led to you. Another possibility comes from the many worlds interpretation of quantum mechanics. In this view, when you make a choice that could create a paradox, you don't change your own past, you create a new, parallel timeline. If you go back and prevent your own birth, you simply branch off into a new reality where you won't exist, while your original timeline remains unaffected. This avoids the paradox by creating an endless number of self-consistent, but separate, realities. At the extremes of gravity, our simple, linear understanding of time is pushed to its absolute limit. What does it mean for us? We've journeyed from the familiar to the deeply strange, and we've seen the idea that cause precedes effect begin to dissolve. So what are we to make of this? If the most fundamental rule of our reality is not so fundamental, what does that mean for us? The first thing to say is that in our day-to-day world, the arrow of time flies true and straight. Your actions have consequences in the future, not the past. The classical understanding of causality that allows us to build bridges and plan our lives remains perfectly intact. The breakdown of causality at the extremes doesn't invalidate our experience. Instead, it enriches it. It suggests that the reality we perceive is an emergent property, a user interface for a much more complex underlying system. The fact that causality seems to be violated in these regimes is not a flaw in the universe, it is a clue. It's a signpost pointing toward a deeper theory of physics that we have yet to discover, a theory of quantum gravity that might unite the strange rules of the small with the immense gravity of the large. The questions that arise are profound. Does some of this suggest that the future is, in some way, already written? Or does it imply that our consciousness plays a more active role in solidifying a previously uncertain past? These are not questions with easy answers. They sit at the frontier of physics and philosophy. But what they tell us is that our most basic assumptions about the world are worth questioning. The universe is not required to make sense to our brains, which evolved for survival, not to comprehend the inside of a black hole or the entanglement of a photon. Ultimately, the fragility of causality is a lesson in humility. It reminds us that our understanding is incomplete. The neat, linear story of cause and effect is just that, a story. A useful one, but not the whole story. The places where it breaks down are the frontiers of human knowledge, where the greatest discoveries of the future are waiting. We've talked about how the future might influence the past. This leads to a fascinating thought experiment. If you could send a single piece of information, a stock price, a warning, a piece of advice, to yourself 1 year in the past, what would it be? And what do you think the consequences would be? Let me know your answer in the comments below. I'm genuinely curious to see what you all come up with. And if you enjoyed this journey to the edge of reality, make sure to subscribe and turn on notifications so you don't miss what's coming next. Today, we set out to find the point where causality breaks down. We began with the simple rule that structures our existence. Cause always comes before effect. It's the law that gives us a past, a present, and a future. But we quickly found the first cracks in this foundation, not in deep space, but in the complex, looping systems of our own world. From there, we took the leap into the quantum realm, where the rule was not just cracked, but seemed to operate on a different logic, where an action in the future could appear to determine the behavior of a particle in the past. And finally, we journeyed to black holes, where gravity threatens to fold time back on itself, forcing the universe to choose between forbidding paradoxes or branching into infinite realities. The breakdown of causality is not a failure of the universe. It's a failure of our intuition. It shows us that our common sense view of the world is a fragile veneer, draped over a reality that is profoundly strange and interconnected. The fact that our logic collapses at its extremes is not an ending. It is a beginning. It is a sign that we are standing on the shore of a vast ocean of knowledge, and the greatest adventures are still ahead. The collapse of our most basic rule is not a reason for despair, it is the ultimate invitation to be curious. This shape breaks the laws of physics. In the quiet, theoretical world of physics, some ideas exist not as observable facts, but as tests for the very rules we trust. They are thought experiments, designed to explore the edges of our understanding. One such idea involves a shape. A surface, described by a simple equation, so precisely curved that it poses a profound question about the nature of reality. On this surface, a small object can rest at its peak, perfectly still, for a second, a minute, or 1,000 years. And then, for no reason at all, at a moment of its own choosing, it can begin to move. This is not a story of magic. It is a puzzle born from the foundational laws of physics, a concept suggesting that for centuries, our understanding of cause and effect might have been incomplete. This shape forces us to ask a quiet, but persistent question. Is the universe a predictable machine? Or is there, hidden within its laws, the possibility of an event without a cause? The clockwork universe. To understand why this idea is so unusual, we need to travel back to the late 17th century. It was a time of intellectual change, and at its center was Isaac Newton. Newton gave us more than just the law of gravity. He offered a new way of seeing the universe itself. Before Newton, the cosmos was often seen as a place of mystery. After Newton, it began to look like a grand, intricate, and predictable mechanism. A flawless clockwork, ticking with mathematical precision. This vision of a predictable universe is built upon Newton's three laws of motion. It is these very laws that our strange shape will test. First is the law of inertia. An object at rest stays at rest, and an object in motion stays in motion, unless an external force acts upon it. This simple idea is profound. It removes the possibility of spontaneous starts and stops. For anything to change its motion, there must be a push or a pull. There is always a reason, a cause. Second is the equation. F equals ma. Force equals mass times acceleration. This is the engine of predictability. It establishes that the relationship between a force and the change in motion it creates is exact and measurable. Third, the law of action and reaction. For every action, there is an equal and opposite reaction. This ensures the forces in the universe remain balanced. Every interaction is accounted for. Together, these three laws describe a deterministic world. Determinism is the idea that all events are determined by preceding causes. In a Newtonian world, if you could know the exact position and velocity of every particle in the universe at a single moment, you could, in principle, calculate the entire future. You could also rewind the clock and calculate the entire past. This idea was famously captured by the French mathematician Pierre-Simon Laplace in 1814. He imagined a vast intellect, later called Laplace's demon, that would know the precise location and momentum of every atom. For such an intellect, Laplace wrote, nothing would be uncertain in the future, just like the past would be present before its eyes. We see this principle in our own solar system. We can predict eclipses centuries from now. We send probes to other planets knowing exactly where they will land years in advance. This is possible because planets and probes follow the deterministic rules written by Newton's laws. The forces are known, the masses are known, and the outcomes are fixed. There are no surprises. This worldview suggested a universe where every event was an inevitable link in an unbreakable chain of cause and effect. An effect always follows a cause, and the path between them is direct and unambiguous. It seemed there were no forks in the road. The Newtonian promise of certainty. The promise of this clockwork universe was deeply embedded in the mathematics Newton used. The equations of motion in classical mechanics are a type of mathematics that describes how things change from one moment to the next. The equation F equals ma, for example, describes how an object's velocity will change when a force is applied. The elegance of these equations is that for most familiar situations, they have a unique solution. This is the mathematical guarantee of determinism. If you provide a complete set of initial conditions, the precise position and velocity of an object at a starting time, the equations will yield one, and only one, trajectory for that object for all of time. Imagine a particle at a certain position with a certain velocity. When we apply the laws, it will travel to one specific place a second later. There is no ambiguity. It cannot decide to go to two different places. If you change its initial velocity even slightly, it will follow a different path, but that new path is also unique and completely determined. This stability is the hallmark of Newtonian mechanics. It's important to distinguish this from what we now call chaos theory. We've heard of the butterfly effect, where a small change can lead to a large and unpredictable outcome. This might seem to challenge determinism, but it doesn't. In a chaotic system like the weather, the future is still fixed by the initial state. The problem is our human inability to measure that initial state with perfect precision. The clockwork is still ticking perfectly. We just can't read its hands accurately enough to make long-term predictions. For centuries, the Newtonian promise held. If you know the present perfectly, the future is an open book. Every effect has a cause, and every cause has a single effect. But what if the problem is not in our measurement, but within the laws themselves? What if a perfectly Newtonian system existed where even a hypothetical, all-knowing intellect would be unable to predict the future? This is where we meet the dome. The crack in the foundation, introducing the dome. Our story now arrives in the year 2003, with a philosopher of physics at the University of Pittsburgh named John D. Norton. He was not trying to disprove Newton with a physical experiment. He was doing something more subtle. He was testing the logical consistency of Newtonian mechanics from within, using its own idealized rules. He devised a thought experiment that has been debated ever since. It is known as Norton's dome. Imagine a dome, a solid, rigid surface in a uniform gravitational field. But this is not a simple hemisphere. It has a very specific shape, described by the equation h equals 2/3 of a gram, r caret, 3/2, where h is the vertical distance from the peak, r is the distance traveled along the surface, and g is the acceleration from gravity. The exact equation is less important than the shape it describes. The surface is perfectly flat at its very top, at a single, infinitesimal point, and then curves away from that apex very sharply. Mathematically, the curvature at the exact peak is infinite. The thought experiment continues. We are in a purely theoretical Newtonian world. There is no friction on the dome's surface. Now, we place a tiny, idealized point mass, a small bead, exactly at the apex of the dome. Its initial position is r equals 0, and its initial velocity is 0. It is perfectly at rest. What happens next? Intuition, trained by a lifetime in a world that largely follows Newton's laws, suggests a clear outcome: nothing. The bead will sit there forever. This intuition is well-founded. At the apex, the downward pull of gravity is perfectly balanced by the upward push of the dome's surface. The net force on the bead is 0. And Newton's first law tells us an object at rest stays at rest unless acted upon by a net force. With no net force, the bead should remain at its starting point indefinitely. There is no cause that could produce the effect of motion. This is one possible future for the bead. Let's call it solution A. The bead remains motionless for all time. It is a perfectly valid solution to Newton's equations of motion. It follows the rules, and it makes intuitive sense. For a long time, most would have agreed it was the asterisk-only solution. But John Norton showed this was not the case. He looked closely at the mathematics and found something else. He found that another, entirely different class of solutions also exists, and these are also perfectly compatible with Newton's laws. And this is where the clockwork universe begins to feel less certain. The paradox unveiled. This is the center of the puzzle. According to Norton's analysis, Newton's laws not only permit the bead to stay at rest, but they also permit a second, very strange outcome. Let's call this solution B. The bead sits at rest on the apex of the dome for some amount of time. It could be 5 seconds, or a minute, or a million years. We can call this waiting period T. Then, at the precise moment that this arbitrary time t has passed, the bead spontaneously begins to slide down the dome. The solution has another unusual property. Not only is the time of its movement arbitrary, but the direction it chooses is also arbitrary. It could slide down any of the infinite number of paths away from the apex. The laws of physics provide no reason for it to prefer one direction over any other. Let's be clear about what this means. The initial conditions are identical in every case. The bead is at r equals 0, with a velocity of 0. Yet, the outcome is not unique. The universe has a choice. It can let the bead sit forever, solution A, or it can let the bead start moving at any future time t, in any direction, solution B. From the exact same starting point, infinitely many futures are possible. This presents a deep challenge to the idea of determinism. Now, skepticism is a natural response. This seems like it must violate Newton's laws. But Norton demonstrated that it does not. He provided an explicit equation for the bead's motion after it starts moving. R(t) equals 1/144th t, t caret 4. Using calculus, one can show that this motion, once it begins, perfectly satisfies F equals ma at every point. The acceleration of the bead always matches the force being applied to it by gravity and the dome's surface. But what about the exact moment the motion begins, at time t equals t? At that instant, the bead's position, velocity, and, crucially, its acceleration are all zero. So even at the moment of transition, F equals ma holds true. There is no single instant where you can point to a violation of Newton's laws. This leads to a subtle reinterpretation of causality. We instinctively ask, what caused the bead to move? The paradox suggests there was no cause. Norton argues that we are accustomed to looking for a cause at the first moment of motion. But his analysis suggests there is no first moment of motion. The time t is the asterisk last moment of rest. The motion occurs in the interval of time after t, and for any interval of time, there is no single, first point. There is no single instant at which to seek an initiating cause. The bead moves simply because the laws of physics, in this specific and idealized scenario, allow for it. The rulebook we thought was absolute contains a clause that says, under these circumstances, an event can happen for no reason at all. This is the failure of determinism from within Newton's own system. Even Laplace's demon, with its infinite knowledge, would be powerless to predict what will happen. This is the kind of idea that stretches our intuition. It challenges our deep-seated assumptions about how the world works. It is a quiet journey into physics and philosophy, where simple rules reveal unexpected complexity. Understanding concepts like this, that explore the boundaries of what we know, requires a different way of thinking. That's why I'm happy to have Brilliant.org as the sponsor for this video. Brilliant is an interactive learning platform for math, science, and computer science that teaches you to think like a scientist. Instead of memorizing facts, their courses are built on active, hands-on learning, helping you build a deep, intuitive understanding of complex topics. If the paradox of Norton's dome interests you, you could explore their course on classical mechanics to solidify your understanding of the very laws the dome challenges. Or perhaps you want to see where physics went next, with their courses on quantum mechanics or special relativity. Brilliant's whole approach is about breaking down large subjects into manageable pieces, making learning a process of discovery. To get started for free, and for the first 200 people to use the link in the description, you can get 20% off an annual premium subscription. I highly recommend checking them out. A huge thank you to Brilliant for supporting this channel. The pushback: is it really a paradox? An idea this strange, of course, did not go unchallenged. Many physicists and philosophers have argued that the dome is not a true paradox, but a mathematical curiosity that could not exist in the real world. These objections are as interesting as the paradox itself. The most common objection is that the dome is an impossible idealization. In the real world, you could never create a surface with this exact mathematical shape. There would always be microscopic imperfections. No surface is truly frictionless. No object could ever be placed at a single, infinitesimal apex. Furthermore, real objects are made of atoms, all vibrating with thermal energy. In the real world, there would always be a tiny, unaccounted-for force that would act as a cause. This is all true, but this objection may miss the central point of the thought experiment. Norton's argument was never about a physical object you could build. His point is about the logical integrity of Newtonian theory itself. The dome is an object that lives entirely within the idealized world of Newtonian mechanics, a world where frictionless surfaces and point masses are standard tools. If the theory's own rules lead to an indeterminate result for a legitimate object within that theory, it reveals a fundamental feature of the asterisk theory, regardless of whether you can build it. A more technical objection focuses on the mathematics. To get the indeterminate result, Norton's solution for the moving bead is stitched to the solution for the bead at rest. Some critics argue that for a motion to be truly physical, all of its derivatives, including concepts like jerk and snap, must be continuous and smooth. In Norton's solution, some of these higher derivatives are not continuous at the moment the motion begins. If you add a new rule to Newtonian mechanics, a rule Newton himself never stated, requiring this infinite smoothness, the paradox disappears. This is a valid technical concern, suggesting the problem lies in what mathematical properties we should expect from a physical model. Perhaps the most powerful counter-argument comes from our modern understanding of physics. Quantum mechanics, our best description of the microscopic world, would make this scenario impossible. The Heisenberg uncertainty principle states that you can never know both the exact position and the exact momentum of a particle simultaneously. You could never place the bead perfectly at rest at the apex. There would always be a fundamental quantum uncertainty in its position and motion. This inherent fuzziness would act as the cause, inevitably sending the bead down one side. In the quantum world, the bead was never truly at rest to begin with. So, the critics have valid points. The dome is an idealization, and quantum mechanics would prevent the scenario. But none of these objections completely dismiss Norton's central claim, that the beautiful, clockwork determinism of classical physics has a strange loophole buried within its own mathematical structure. The philosophical fallout. The debate over the dome extends beyond physics, touching on quiet questions about the nature of reality itself. What is a cause? What is a law of nature? And what does it mean for a theory to be deterministic? For centuries, cause and effect has been a cornerstone of how we understand the world. Newton's laws seemed to elevate it to a universal principle, woven into the fabric of the cosmos. Norton's dome challenges this. It presents a scenario where the laws and the initial state are perfectly known, and yet no specific effect must follow. It suggests that causality might not be a fundamental law, but rather what Norton calls a folk science, a useful rule that applies to most everyday systems, but not a universal truth. This leads to a re-evaluation of what we expect from our physical theories. We tend to believe the laws of physics should be prediction machines. But the dome suggests that perhaps this is not their only function. Perhaps the laws of nature are not entirely prescriptive, telling the universe what it must do, but are sometimes permissive, merely outlining what is possible. In this view, Newton's laws simply state that both staying put and moving are possible outcomes. The laws permit the motion, but they do not compel it. The paradox also makes us question the role of mathematical idealizations in science. Physics is filled with them: massless ropes, frictionless planes, spherical planets. We use these to make the math manageable. Usually, we assume these are gentle approximations. The dome is different. A dome with any finite curvature at its peak, like a hemisphere, is perfectly deterministic. It's only at the absolute limit of infinite curvature that determinism breaks down. This suggests some idealizations may introduce behaviors that have no counterpart in the physical world. Ultimately, the philosophical consequence of Norton's dome is that it reveals the hidden assumptions in our scientific worldview. We assume causality is universal. We assume laws must be deterministic. The dome, whether a true paradox or a mathematical curiosity, is a reminder that these are, in fact, assumptions. It peels back a layer of certainty, revealing the complex and sometimes counterintuitive relationship between our mathematical descriptions and the world itself. Beyond Newton, the bigger picture. While the dome is a puzzle within classical mechanics, its importance may lie in how it prefigures the stranger ideas of modern physics. The crack it reveals in Newtonian determinism is a faint tremor compared to the changes brought by relativity and quantum mechanics in the 20th century. In a way, the dome is a quiet introduction to the universe's inherent strangeness. It shows that even in the world of simple pushes and pulls, the relationship between cause and effect can be subtle. This prepares us for the more profound ways modern physics dismantled the clockwork universe. Einstein's theory of relativity altered our understanding of space, time, and causality. But the true end of classical determinism came with quantum mechanics. As we touched on earlier, the quantum world is fundamentally probabilistic. When a radioactive atom will decay is not just unknown, it is unknowable. It is a matter of pure chance. Unlike the dome, which is a very specific and idealized scenario, quantum indeterminacy is a fundamental feature of reality. Looking at the bigger picture, Norton's dome can be seen as a kind of classical echo of this modern weirdness. It is like a ghost of quantum mechanics haunting the classical machine. It shows that the seeds of indeterminism were already there, buried deep in the mathematics of Newton's own laws, waiting for a peculiar enough shape to bring them to light. It highlights a recurring theme in science. Our theories are often stranger than their creators imagined. Newton built a clockwork universe, but the mathematics he used contained the blueprint for a shape that could quietly challenge it. We have journeyed to the peak of a strange, imaginary shape and looked at a deep question about predictability. We've seen how a single, careful thought experiment can challenge a scientific idea that has stood for over 300 years. Norton's dome shows that the deterministic, clockwork universe of Newton and Laplace may have a loophole. It reveals that within the framework of classical mechanics, a scenario exists where an event can occur without a cause, and where the future is not uniquely determined by the present. We've also seen the careful debate it has started. Is it a true failure of determinism, or a mathematical artifact? There is no final consensus. That ongoing discussion is perhaps its greatest value. The dome acts as a stress test for our understanding. It forces us to be more precise about what we mean by cause, law, and determinism, and reminds us that the universe is not obligated to fit our intuitions. This shape may not break the laws of physics, but it does break our simple interpretations of those laws. It reveals a hidden depth, a surprising ambiguity, in a system we thought we understood completely. It teaches us that even the most solid foundations of science can have subtle cracks, and looking into those cracks can lead to some of the most interesting questions we can ask. It leaves us with a final thought to consider. If a system this simple can contain such a fundamental unpredictability, what other quiet possibilities might be hiding in the more complex laws that govern the rest of our reality? Thank you for joining me on this exploration into one of physics' quiet paradoxes. If this kind of calm exploration into science helps you unwind, consider liking the video and subscribing to the channel. I would love to hear your thoughts in the comments below. Are you convinced by Norton's argument, or do you think the objections resolve the paradox? A special thank you to my patrons on Patreon who help make these videos possible. If you'd like to support the channel directly, you can find the link in the description. Thank you again for watching, and as always, stay curious. Einstein's one law that prevents total chaos. Imagine you receive a message. It arrives not from across the ocean, but from across time, a complex string of data from the future, containing a warning that helps prevent a catastrophe said to happen tomorrow. You act on it, and the world is saved. But a quiet question should follow. If you prevented the catastrophe, it never happened. If it never happened, there was no reason for anyone in the future to send a warning. So, where did the information come from? This isn't just a plot from a story. It's a logical knot, a contradiction that seems to pull at the very fabric of how we believe reality works. It's a kind of loop the universe cannot easily resolve. In effect, the message would exist without its cause. This kind of unraveling, where the coherent story of the cosmos begins to fray, could be our reality, a world of uncaused events and impossible feedback loops, if not for a single, deeply elegant principle. A law Albert Einstein uncovered that, almost as a quiet consequence of its main purpose, stands as a guardian against this kind of chaos. It is the one principle that holds the line, and keeps the story of the universe written in a language that makes sense. The pillar of reality. Before we can meet the guardian, we must first understand the principle it protects: causality. It's a concept so fundamental, so intuitive, we rarely give it a second thought. An effect cannot happen before its cause. It is the simple, steady sequence that governs our lives. You flip a switch, and then the light turns on. A line of dominoes falls, one after the other, in a predictable chain. You see a flash of lightning, and you know, with a quiet certainty, that the sound of thunder will follow moments later. It is never the other way around. This sequence, cause then effect, is more than just a preference for order. It is the foundation of logic, the ground upon which our understanding of the universe is built. In a very real sense, it is the arrow of time itself. For us, time doesn't just pass. It flows in one direction, from a settled past, through a fleeting present, toward an open future. Physicists visualize this journey as a world line. Imagine a four-dimensional graph, with 3 dimensions for space and 1 for time. Your entire life, from beginning to end, is a continuous, unbroken line tracing a path through this block of spacetime. Every event on that line, every thought, every decision, occurs in a strict, unalterable order. The event of you deciding to watch this video happens before the event of you hearing these words. One point on your world line causes the next. This isn't just an observation, it's a pillar of classical physics. From Newton's laws to thermodynamics, the assumption that the past shapes the present, and the present shapes the future, is woven into the mathematical fabric of reality. It's what allows us to make predictions, to conduct experiments, and to build things that work. Without the reliable chain of causality, science itself would be difficult to imagine. How could you trust the result of an experiment if the outcome could appear before you've even begun? For centuries, this principle was treated as an axiom, a self-evident truth. It was simply the way the world worked. The universe was seen as a great clockwork machine, set in motion at the beginning of time and ticking along predictably, each gear turning the next in a perfect causal sequence. But as the 20th century began, a quiet revolution in physics started to stir. Questions once considered strange began to be asked by serious minds. Is this law of cause and effect truly absolute? Or is it just a habit of our particular corner of the cosmos? To understand that, we must venture into a thought experiment, a journey into a world where the most basic rule of reality is broken. The unraveling, a universe of paradoxes. Let's take that journey now. Let's imagine a universe where the law of causality is not firm. A reality where an effect can precede its cause. It sounds like a subtle change, a minor edit to the operating system of the cosmos. But the consequences are profound. It wouldn't just be a strange universe. It would be a logically unstable one, a reality that constantly seems to refute its own existence. First, let's explore the most well-known temporal puzzle, the grandfather paradox. Imagine you build a machine that can travel through time. You intend to go back and witness a historical event, But you arrive in the year your grandfather was a young, unmarried man. In a strange, tragic accident, you inadvertently cause his untimely death before he has a chance to meet your grandmother. The consequence is immediate. Your father is never born. If your father is never born, then you are never born. And if you are never born, you could never have built the time machine. And if you never built the time machine, you could never have gone back in time to cause the accident. This means your grandfather lives, meets your grandmother, your father is born, and then you are born, eventually building a time machine. The universe is now caught in an endless, oscillating loop of contradiction. It's a state of being and not being. The universe cannot simultaneously contain both your existence and your non-existence. It's a paradox that reality itself cannot resolve. But it gets even stranger. Let's revisit the puzzle from our introduction, a kind of information paradox often called a bootstrap paradox. Imagine a composer struggling with writer's block. One day, a mysterious stranger visits him and hands him a book filled with the most beautiful symphonies ever conceived. The composer spends his life performing these works, becoming world famous. On his deathbed, he instructs his assistant to take the original book and, using a time machine, give it to his younger self on a specific day. The assistant does so, traveling back and becoming the mysterious stranger. Here is the quiet, unsettling question. Where did the music come from? The young composer received it from the old composer. The old composer received it from his younger self. The information, the music itself, exists in a closed loop with no point of origin. It was never created. It was never composed. It simply is. This pulls at the idea that information, like energy, cannot be created from nothing. The music is an effect without a cause. It bootstrapped itself into existence. A universe filled with such paradoxes would be one where knowledge and art could exist without ever being invented, a sea of unauthored information. The implications go beyond just time travel. If causality is not fundamental, even everyday events become suspect. Imagine sitting in your room. A baseball flies through the air, and your window shatters. Cause and effect. Now, imagine the window shatters first, the glass exploding inward for no reason. A second later, a baseball appears out of thin air outside the now broken window and flies away from your house. This is a universe with uncaused effects. It's a world where things happen for no reason at all. In such a universe, the very concept of a physical law would become uncertain. The consistency we rely on would be replaced by an arbitrary reality where anything could happen at any moment. It is a universe of pure chaos. A reality that, in a very literal sense, cannot compute itself because its own history is a stream of logical errors. This is the abyss. And standing guard at the edge of that abyss is a single, astonishingly simple feature of our universe. The elegant architecture. So, how does the universe save itself from this paradoxical unraveling? The answer lies not in some complicated rule, but in a profound insight from Albert Einstein in 1905. It's the great solution to the problem of chaos, and it is this: there is a cosmic speed limit. The principle that prevents this chaos is that the speed of light in a vacuum, a constant known as c*, is the absolute maximum speed at which anything, any object, any information, any causal influence, can travel. On the surface, this might seem like just a rule about velocity. But its implications are far deeper. This speed limit is not just a traffic law for the cosmos. It is a fundamental design principle of causality itself. To understand how, we need to adjust our view of the universe, just as Einstein did. We must stop thinking of space and time as separate things. They are not. They are two aspects of a single, unified fabric called spacetime. Every event is a point in this four-dimensional block. Your world line is your path through it. Now, here is the crucial insight from Einstein's theory of relativity. Observers moving at different speeds will disagree on measurements of distance and the passage of time. For someone moving quickly past you, your ruler would seem shorter, and your clock would seem to tick slower. But amidst this relativity, Einstein found one thing that was absolute, one thing every observer could agree on: the asterisk spacetime interval. This is a special way of measuring the separation between two events that combines both their distance in space and their separation in time. It is the one true, unchanging measure of the relationship between events. And this invariant interval is what creates the universe's causal geography. It defines the fundamental layout of what can affect what. To visualize this, we can use one of the most powerful concepts in physics: the asterisk light cone. Imagine an event happens. You snap your fingers right here, right now. That event is the sharp point of a cone. Now, imagine light spreading out from that snap in all directions. As time moves forward, that sphere of light expands. If we plot this on a spacetime diagram, with space as the horizontal axis and time as the vertical axis, the expanding sphere of light traces out a cone pointing upwards. This is the asterisk future light cone. It contains every single point in spacetime that can possibly be influenced by your finger snap. Anything outside this cone is too far away for light, or any signal, to have reached it yet. Similarly, there is a cone pointing downwards. This is the asterisk past light cone. It contains every event in the past that could have possibly had an effect on your finger snap. It's the set of all possible causes. Everything outside both cones is a region called elsewhere. Events in elsewhere are fundamentally, causally disconnected from your finger snap. They cannot affect it, and it cannot affect them. The light cone isn't just a helpful diagram, it's a physical boundary. Now, we can finally see how this elegant geometry prevents chaos. For an effect to precede its cause, to receive a message from the future, information would have to travel from a point inside your future light cone back to you in the present. On a spacetime diagram, this path would have to be tilted more horizontally than vertically. And to travel on such a path requires moving faster than the speed of light. Because nothing can travel faster than light, you are physically, geometrically trapped within the future light cone of all your past events. You cannot escape it. The grandfather paradox is resolved because you simply cannot travel to a point outside the future light cone of your own existence. The bootstrap paradox is resolved because information from the future cannot travel backward in time to create a loop. This is the quiet beauty of Einstein's discovery. Causality is not a rule added on top of physics. It emerges from the geometry of spacetime itself. The universe doesn't need a separate rulebook to prevent paradoxes. The very shape of reality makes them impossible. The cosmic speed limit is the law of causality in disguise. The architecture of spacetime is the guardian. The quantum wrinkle. So, the case seems closed. The rigid geometry of spacetime, described by relativity, has locked down the principle of causality. The speed of light stands as an unbreakable barrier, its light cones defining the absolute boundaries of cause and effect. It's a perfect, elegant system. Well, this is physics. And just when you think you have a perfect system, you discover the quantum world. And in the quantum world, the rules get fuzzy. The wrinkle in our story comes from a phenomenon that famously unsettled even Einstein himself, a phenomenon he called spooky action at a distance. Today, we call it quantum entanglement. Here's the concept. It is possible to create two particles, say, two photons, that are intrinsically linked. Their properties are tied together in a shared quantum state. For example, if you measure one and find its spin as up, you will know, with 100% certainty, that its entangled partner, no matter where it is, will have a spin of down. The spooky part is this. According to quantum mechanics, before you measure it, the particle doesn't have a definite spin. It exists in a probabilistic haze. The moment you measure the first particle, its state collapses into a definite reality, up. And in that exact same instant, its partner, which could be light years away, also collapses into the opposite state, down. This is what was so unsettling. It appears as if some kind of signal, the result of the first measurement, is traveling between the particles instantaneously, far faster than the speed of light. It seems to be a clear violation of the cosmic speed limit, the very principle that protects causality. Did we just find a loophole? The answer, according to our current understanding, is a firm and fascinating no. While the correlation is instantaneous, it cannot be used to transmit usable, controllable information faster than light. Here's why. You have no control over the outcome of your measurement. The result you get, up or down, is fundamentally random. You can't force it to be up just to send a 1 to a friend with the other particle. All you get is a random bit. Your friend, measuring their particle, also gets a random bit. Neither of you has any usable information until you communicate your results later through a conventional, slower than light channel, like a radio signal. Only when you bring your two lists of random results together can you see the spooky pattern. Causality is safe, but this is where the story pivots from a clean resolution to a deeper mystery. While we can't use entanglement to send messages to the past, it does show us that the universe at its most fundamental level is non-local. There are connections that seem to transcend space in a way our intuition struggles with. It suggests the neat separation of events into here and there might be an illusion. And some areas of theoretical physics push this fuzziness even further. When we try to merge Einstein's theory of gravity with quantum mechanics, things get stranger still. Some theories of quantum gravity suggest that at the tiniest possible scale, spacetime itself is not a smooth fabric. It may be a chaotic, quantum foam, where concepts of before and after lose their meaning. In this realm, the light cones that so rigidly define causality might themselves become probabilistic and fuzzy. These are still speculative ideas, but they show that the relationship between spacetime and causality is extraordinarily subtle. So, while the grand architecture of relativity prevents the chaos of macroscopic paradoxes, the quantum world introduces a profound wrinkle. It upholds the law, no sending controllable messages to the past, but it redefines the spirit of it. It tells us that while causality is protected, the clear, sharp line we draw between a cause and its effect might be an emergent property of a much weirder, more interconnected, and fundamentally fuzzier quantum reality. The guardian of reality. Our journey has taken us from a simple, intuitive rule to the deepest frontiers of modern physics. We began with the bedrock principle of our reality. Cause must always precede effect. It's the simple, linear story that allows our universe to make sense. Then, we imagined a universe without this pillar, a reality of self-negating paradoxes and uncaused events, a cosmos descending into logical chaos. And from that chaos, we found the elegant solution in Einstein's work. The cosmic speed limit is not just a rule about speed. It is woven into the very geometry of the universe. It forges the structure of spacetime itself, creating the inviolable boundaries of the light cone, the physical manifestation of causality. This structure is the guardian of reality, a built-in feature that ensures the logical consistency of the cosmos. Yet, just as we found comfort in this order, the quantum world introduced a fascinating twist. Through the spooky lens of entanglement, we saw that while the transmission of usable information is locked behind the speed of light, the universe possesses a deep, non-local interconnectedness. We learned that the crisp line between cause and effect, so absolute on our scale, might blur into a probabilistic haze at the fundamental level of reality. We are left, then, with a stunning duality. On the grand scale of stars and galaxies, causality is protected by the rigid geometry of relativity. But on the infinitesimal scale of quantum mechanics, the relationship between cause and effect becomes a deeper, stranger mystery. The architecture of spacetime prevents the chaos of paradoxes, but it does so by pointing us toward an even more profound truth. Our simple, linear understanding of this caused that may only be the surface of the story. The guardian of reality not only protects our ordered universe, but it also stands as a quiet signpost, directing our curiosity toward the next great mystery, the true nature of time itself. If this kind of calm exploration into the nature of reality helps you unwind, consider liking the video and subscribing to the channel. And I have to ask, if causality wasn't a factor, and you could send one quiet message to the past, what would it be? Let me know in the comments below. Why you and I live in different timelines. What if I told you that right now, you and I are living in different timelines? That our shared idea of now is just a stubborn, comfortable illusion? What if I said that if we both watched two things happen, we could honestly and correctly disagree on which one came first? This isn't a mistake. It's not a philosophy riddle or a trick of our eyes. It's a fundamental, mind-bending feature of the very fabric of our universe, where time is deeply personal and a universal now is a myth. And the key to getting this doesn't come from some crazy complex lab. It all comes down to a simple story. A story about a train, two bolts of lightning, and a complete reimagining of reality itself. By the end of this, you won't just understand why time is relative, you'll feel it. And you'll see that the universe is far stranger, and way more elegant than our common sense could ever lead us to believe. The comfortable lie. For almost all of history, we had a pretty simple, comforting idea about time. It was the universe's master clock. Picture this grand, invisible metronome, ticking away the moments of existence, one by one, for every single thing in the cosmos. All at the same time. Whether you were in ancient Rome, on the surface of Mars, or in a galaxy a billion light-years away, that clock ticked in perfect sync for everyone. This was the world according to Isaac Newton. In Newton's universe, time was like a river, flowing forward at the same constant rate for everything and everyone. My now was your now. If I saw a firework explode and then heard the bang, anyone, anywhere, would agree the explosion happened before the sound. The order was fixed. Event A happens, then event B happens. End of story. This idea is more than just old science, it's hardwired into our intuition. It's how we experience the world every day. When you watch a race, someone wins by crossing the finish line first. No ambiguity there. You drop a glass, it falls, and then it shatters. The cause always comes before the effect. This straight line, absolute sequence of events feels true because, on a human scale, it works perfectly. Our brains evolved in a world of slow speeds and manageable distances. For centuries, this was the bedrock of physics. It was so powerful it could predict the motion of planets with stunning accuracy. It gave us a shared reality where, before, and after, were universal truths. Time was the one reliable thing that never changed. But science is all about poking at the edges of what we think we know. And at the turn of the 20th century, a few brilliant people started poking at the nature of light. The question seemed simple, but the answers didn't just crack the foundation of absolute time, they shattered it. They found that the universe's one true constant wasn't a cosmic clock, but something far, far stranger. And in doing so, they showed that the river of time wasn't one single flow, but a vast delta of infinite, personal streams. The cosmic speed limit. So, what broke our comfy idea of time? It all started with a question. What happens when things move, really, really fast? In the mid-1800s, the physicist James Clerk Maxwell unified electricity and magnetism into a single set of beautiful equations. But buried inside his own math was a startling prediction: electromagnetic waves that traveled at a very specific speed, about 300,000 kilometers per second. This was the speed of light. But here's the profoundly weird part. The equations didn't say what this speed was relative to. Usually, speeds are always relative. If I'm on a train going 100 kilometers per hour and throw a baseball at 20 kilometers per hour, someone on the ground sees the ball moving at 120 kilometers per hour. Simple addition. That's how we think things work. Maxwell's equations just said the speed of light is c. Period. This created a huge puzzle. Was it relative to the flashlight? The Earth? Some invisible cosmic jelly they called the luminiferous ether that was supposed to fill all of space? Scientists scrambled to find this ether. The famous Michelson-Morley experiment was designed to detect the Earth's motion through it by measuring the speed of light in different directions to see if it changed. The result? Nothing. Absolutely nothing. It was a spectacular failure that became one of the most important experiments in history. It seemed that no matter how you moved, or how the source of light moved, a beam of light would always zip past you at the exact same speed. Think about that. You're in a rocket ship blazing along at half the speed of light, an insane 150,000 kilometers per second. You turn on your headlights. Common sense says someone watching from a planet should see that light beam moving at 1.5 times the speed of light. But they don't. They measure it and get exactly c. And weirder still, you, inside your rocket, also measure the light from your own headlights moving away from you at c. This is completely bonkers. It's like running after a car and, no matter how fast you run, it's always pulling away from you at the same speed. How is that possible? This is where a young patent clerk in Bern, Switzerland, enters the story. In 1905, Albert Einstein was obsessed with this paradox. While everyone else tried to shoehorn this weird fact about light into the old rules, Einstein did something much bolder. He decided to trust the paradox. He started with two simple-sounding ideas. First, the laws of physics are the same for everyone moving at a constant velocity. If you're in a smooth-moving train with the windows blacked out, you can't tell if you're moving or standing still. Second, the bombshell. The speed of light in a vacuum is the same for all observers, no matter how they're moving. Einstein realized that if the speed of light is the one thing that never changes, then something else must. That something else was space and time. To keep the speed of light constant for everyone, space has to contract, and time itself has to slow down or speed up. It had to become flexible, personal. And just like that, he threw out the master clock of the universe and gave each of us our own. The train and the lightning. Okay, this is the core of it. This is where we see how a constant speed of light blows up the idea of a universal now. To get there, we're going to use Einstein's favorite tool, a Gedanken experiment or thought experiment. Let's build it together, and I want you to put yourself right in the middle of it. First, imagine you're standing on a train station platform, positioned very, very carefully right at the exact midpoint. Now, a long, futuristic train is about to blast past you at an incredible speed, say, 80% of the speed of light. Just as the very center of the train is perfectly lined up in front of you, a dramatic event happens. Two massive bolts of lightning strike the tracks simultaneously. One hits the track at the very front of the train, and the other hits at the very back. From your perspective on the platform, these two events are undeniably simultaneous. You're the perfect judge because you're standing at the exact halfway point. The light from the front strike and the light from the back strike have to travel the exact same distance to reach your eyes. Since the speed of light is constant, the two flashes arrive at your retinas at the exact same instant. Your conclusion is simple and logical. The lightning struck at the same time. For you, these events share the same now. They are simultaneous. Lock that in. That is your reality. But you're not the only one watching. Let's put your friend on this super fast train. And just like you, she is sitting right in the exact center of her train. At the precise moment she passes you, the instant the center of the train aligns with the center of the platform, the two bolts of lightning strike. From your perspective, those strikes were simultaneous. But what does your friend on the train see? What is her reality? This is where everything changes. As the light from those strikes races towards her, your friend isn't standing still. The train is rocketing her forward. This means she's moving towards the spot where the front lightning bolt struck, and moving away from where the rear one struck. So, the light from the front strike is racing towards her, but she's racing to meet it. The distance this light needs to cover to reach your eyes is shortened. It gets to her super fast. Now, think about the light from the rear strike. It's also racing towards her at the speed of light, but she's fleeing from it. The light has to play catch up as she moves forward. The distance this light must cover is much longer. It's going to take more time to get to her. So what's the result? The flash of light from the front strike reaches your friend's eyes first. A moment later, the flash of light from the rear strike reaches her. Now, your friend is just as smart as you are. She knows she's in the middle of the train, and she knows with absolute certainty that the speed of light is constant. Given these facts, that light from the front got to her first, light from the back got to her second, and she's in the middle, what can she possibly conclude? Her conclusion is just as logical and inescapable as yours. The lightning must have struck the front of the train before it struck the back. For her, the events were not simultaneous. Let that sink in. You, on the platform, saw two events happen at the exact same time. Your friend, on the train, saw one of those events happen before the other. Who is right? The stunning, reality-shattering answer of relativity is that you both are. There is no single, true answer. Simultaneity isn't a property of the events themselves. It's a property of the relationship between the events and whoever is looking at them. Your now is one slice through reality that is valid for you. Her now is a different slice through reality, tilted relative to yours, that is equally valid for her. This isn't a trick or an illusion. It's a fundamental consequence of the one fixed law. The speed of light is constant for everyone. To protect that law, the universe gives up on the idea of a universal now. If your brain feels a little scrambled right now, good. That is the correct response. This one-thought experiment dismantled a 200-year-old pillar of physics and changed our understanding of reality forever. It reveals a universe that is profoundly more personal than we ever imagined. And if you enjoy having your perception of reality fundamentally rearranged like this, it's what we do here all the time. Taking a second to subscribe ensures you won't miss our next journey to the edge of what's known. It really helps us make more deep dives into the biggest ideas in science. Now, let's get back to it, because this apparent chaos raises an even bigger question. Does this break reality? Okay, but wait. The immediate, terrifying question is, if the order of events is up for grabs, what happens to cause and effect? If you can see A happen before B, and I can see B happen before A, can a window shatter before the rock hits it? This is the problem of causality, the most sacred rule of the universe. The cause must always come before the effect. If relativity destroyed this, it would create a universe of paradoxes. The answer is a deep, profound, and incredibly elegant no. And the reason it doesn't break causality is maybe the most beautiful concept in all of special relativity, the light cone. To protect causality, the universe has a built-in safety mechanism. To see it, you have to stop thinking of space and time as separate things and start thinking of them as a unified, four-dimensional fabric called spacetime. Now, imagine an event. Say, you snapping your fingers. From that single point in spacetime, picture a cone opening up into the future. The walls of this cone are defined by the path of a flash of light expanding outwards from that snap. This is your future light cone. Anything that happens inside this cone is a place and time that can be affected by your snap. A signal, moving at or below light speed, can get from your event to any event inside this future light cone. Now, imagine another cone, opening into the past. This is your past light cone. It represents all the events in space-time that could have possibly affected you, right now. Here's the crucial part. What about everything outside of these two cones? This vast region is called elsewhere. Any event that happens in the elsewhere is causally disconnected from you. It's too far away in space and too close in time for any signal, even light, to have traveled between you and it. You cannot affect it, and it cannot affect you. This is the universe's safeguard. This is what saves causality. Let's go back to the train. Those two lightning strikes are separated by a large distance in space. Because of this, they lie outside of each other's light cones. They're space-like separated. And because they have no causal relationship, one couldn't have caused the other. The universe literally does not care which one came first. Their order is ambiguous because their order is irrelevant. Now, let's take two events that are causally linked. I throw a rock, event A, and it smashes a window, event B. The window shattering is squarely inside the future light cone of me throwing the rock. These events are time-like separated. And for any two events that are time-like separated, something magical happens. Every single observer in the universe, no matter how fast they're moving, will agree on their order. Everyone sees the rock thrown before the window shatters. The order of causally connected events is absolute and protected. So, relativity doesn't destroy causality, it clarifies it. The law of cause and effect is simply the law that an effect must lie within the future light cone of its cause. The whole, your now is not my now, thing only applies to events that can't affect each other anyway. So rest easy. You will always see the effect follow the cause. The block universe. When we step back and look at what all this means, we are forced to see the universe in an even stranger, more beautiful way. One of Einstein's former teachers, Hermann Minkowski, was the first to fully grasp what this all meant geometrically. He realized that space and time aren't separate things at all. They're woven together into a single four-dimensional fabric, spacetime. In this view, you're not a three-dimensional being moving through time. You are a four-dimensional world line, an object stretching through spacetime from your birth to your death. And here's a wild thought. Every single one of us is always moving through spacetime at one constant speed, the speed of light. If you are standing perfectly still in space, you are hurtling through the time dimension at the maximum rate. But as soon as you start to move through space, you have to trade some of that speed from the time dimension for speed in the space dimension. This is why moving clocks run slow, it's called time dilation. You're literally trading motion through time for motion through space. Your individual, now, is just your personal slice through this four-dimensional block of spacetime. An observer moving relative to you is just taking a different slice, at a different angle. My slice might contain two events I call simultaneous. Your slice, tilted relative to mine, might cut through those same two events at different points on their time axis, so you see them happen at different times. This leads to a powerful, and kinda unsettling, philosophical idea known as the block universe. If spacetime is a single four-dimensional structure, it suggests that the past, present, and future all exist in the same way. Everything that ever has happened and ever will happen is already embedded within the geometry of the block. Our feeling of the flow of time is just our consciousness moving along our world line, like a spotlight illuminating one moment at a time on a vast, static sculpture. So, we started with a comfortable illusion, a universal clock ticking for us all. We saw how the universe's one stubborn constant, the speed of light, forces us to throw that clock away. This led us to the relativity of simultaneity, the strange fact that your now is not my now. And just when it seemed like this might break reality, we saw how the universe protects the sacred law of cause and effect with the beautiful geometry of light cones. You and I may live in different timelines, our present moments just different slices through a grander four-dimensional reality. But we are still bound together by the same unbreakable laws of causality that give the universe its structure. It leaves us with a final, staggering thought. If the order of some events is just a matter of perspective, what does that say about the past and the future? Is it all already written in the fabric of spacetime, and we are just experiencing the pages of the story, one by one? If this trip through spacetime bent your mind in the best possible way, you might really enjoy our video on its sister concept, time dilation and the famous twin paradox. You can click here to watch that next. And I genuinely want to know what you think, so tell me in the comments. What is the single most counterintuitive part of this for you? For more trips to the edge of reality, make sure to subscribe. Science just proved the future can influence the past. Imagine standing in a quiet laboratory. On a table before you sits a simple box. A single particle of light, a photon, was just sent through it, where it interacted with two processes before coming out the other side. The event is over. It has already happened. The past, as we have always understood it, is settled. But what if a choice you make, right now, could reach back and define the very nature of that past event? What if your decision determines whether the photon experienced those two processes in a neat, orderly sequence, or if it experienced them in a strange quantum state where both orders happened at the same time? This isn't a thought experiment. It's a gentle description of a real phenomenon, demonstrated in laboratories around the world. It's called indefinite causal order, and it quietly challenges the foundation of our reality. The idea that a cause must always come before its effect. Science is now showing us that the straight line we imagine for time, first this, then that, might only be a story we tell ourselves. The universe, at its most fundamental level, seems to be far more strange and the relationship between the past, present, and future more deeply connected than we ever imagined. The clockwork and the cloud. Our entire experience of the world is built on a simple, steady assumption: the arrow of time. Time flows in one direction. A glass falls, and then it shatters. Lightning flashes, and then thunder rolls. Cause and effect are the quiet rails that reality runs on, a sequence that has seemed unbreakable since the beginning of everything. This is our classical intuition, and for centuries, it felt as solid as the ground beneath our feet. Classical physics reinforced this feeling. The universe was seen as a great clockwork, a predictable machine. If you knew where every piece was at one moment, you could, in theory, calculate the entire future and reconstruct the entire past. Everything had a before, and everything had an after. Then, at the turn of the 20th century, a small crack appeared in this perfect clockwork. That crack was quantum mechanics. The solid, predictable world dissolved into a shimmering cloud of possibilities. A particle, like an electron, was no longer a tiny, definite thing. It was described by a wave function, a mathematical expression of all its possible states existing at once. This is the principle of superposition, famously seen in the double-slit experiment, where a single particle seems to pass through two separate slits at the same time, behaving like a wave. When we observe the particle, this cloud of possibilities collapses into a single, definite reality. This strange duality, existing in multiple states at once until measured, was the first clue that the quantum world doesn't play by our rules. But for a long time, this strangeness was thought to apply only to a particle's properties, like its location or its spin. The timeline itself, the sacred order of events, was believed to be immune. Some physicists, most famously Albert Einstein, resisted these ideas. He believed there must be some hidden information, a pre-written script that our measurements were simply uncovering. He argued for a locally real universe, where things have definite properties and can only be influenced by their immediate surroundings. This debate continued until the 1960s, when physicist John Bell designed a mathematical test, now known as Bell's theorem. This test could experimentally distinguish between Einstein's classical view and the strange predictions of quantum mechanics. The results were revolutionary. Bell's theorem, confirmed by countless experiments, proved Einstein's classical intuition wrong. The weirdness is real. The universe is fundamentally non-local. Two entangled particles, separated by vast distances, can be linked in a way that defies any classical explanation. This discovery opened a new door. If the universe isn't locally real, and separated events can be connected in ways that defy classical space, what about time? If a particle's properties aren't fixed until we measure them, what if the causal order between events isn't fixed either? What if before and after is just another quantum property that can exist in a superposition? This question, once speculative, has now moved into the laboratory. And the answer scientists are finding is a quiet but profound yes. The quantum switch. Where before and after coexist. To understand how the nature of the past can be defined by the present, we need to look at a real experimental device known as the quantum switch. The concept is both brilliantly simple and deeply perplexing. It is the machine that allows the timeline to bend. Imagine, again, our single photon. We send it on a journey through two gates, which we can call Operation Alice, A, and Operation Bob, B. These could be anything. A filter that changes the photon's polarization in one way, and another that changes it differently. In our normal world, there are only two possibilities. The photon passes through Alice and then Bob, a right-pointing arrow B, or it passes through Bob and then Alice, B right-pointing arrow A. The order is fixed. The quantum switch introduces a new element, a control qubit. A qubit is the quantum version of a computer bit. While a classical bit is either a 0 or a 1, a qubit can be a 0, a 1, or both at the same time, thanks to superposition. The path the photon takes is now determined by the state of this control qubit. If the control is in the state 0, the photon is routed through Alice, then Bob. The sequence is a right-pointing arrow B. If the control is in the state 1, it is routed through Bob, then Alice. The sequence is B right-pointing arrow A. So far, this is just a clever router. But here is where the quantum leap happens. What if we prepare the control qubit in a perfect superposition of 0 and 1? According to quantum mechanics, the photon now travels both paths at once. The event, Alice acts on the photon, is happening both before and after the event, Bob acts on the photon, in the same experiment, at the same time. It's important to understand this isn't a case of us simply not knowing the order. In an experiment by Giulia Rubino and a team at the University of Vienna in 2017, they showed that the very concept of a definite order did not exist within their system until a final measurement was made. The order itself becomes what physicists call indefinite. Now for the part that stretches our minds. The photon passes through this entire apparatus, existing in a superposition of A then B and B then A, and then travels on. The control qubit travels with it. The event inside the switch is, for all intents and purposes, over. It has happened, but the final step is a choice made by the experimenter. In the future, relative to the photon's journey, the experimenter chooses how to measure the control qubit. They can choose to ask, were you a 0 or a 1? When they do this, the superposition is broken, and the system is forced to pick one reality. The result will correspond to either the A right-pointing arrow B path or the B right-pointing arrow A path. It's as if we've opened a book and found the story was written one way or the other all along. But the experimenter can make another choice. They can perform a different kind of measurement, one that asks, were you in a superposition of 0 and 1? By making this measurement, they reveal the consequences of the photon having been in asterisk both orders at once. The outcome of this measurement can only be explained if the photon truly experienced an indefinite causal order. And here is the quiet revelation. The choice of measurement made by the experimenter now, after the photon has already passed through the gates, defines the nature of the event that happened in the past. If they choose to measure the 0 or 1 foot basis, they are effectively ensuring the past event must be described as having had a definite, though random, order. If they choose to measure the superposition basis, their choice ensures the past event must be described as having had an indefinite order. A choice made today defines the causal nature of an event that occurred yesterday. This doesn't mean you can send a message to change the past. The outcome of any single measurement is still random. The effect is only visible statistically after running the experiment many times. It is a subtle, statistical link, but a link nonetheless. It shows the boundary between past and future is not a solid wall, but a porous border, where a future choice about how to ask a question can shape the very structure of the events being questioned. An even more mind-bending version of this was proposed by Magdalena Zeitch at the University of Queensland, called the gravitational quantum switch. In this thought experiment, the control is the position of a massive object, like a star. According to general relativity, time flows at different rates depending on gravity. If the star is in a superposition of two locations, it creates a superposition of spacetime itself. Two events, Alice and Bob, would each be in a state of both being before and after the other, because the very fabric of time they are embedded in is indefinite. This suggests indefinite causal order may be a fundamental feature of a universe that is both quantum and gravitational. The fingerprint of a broken timeline. A claim this extraordinary requires extraordinary evidence. How can physicists be so certain the causal order is truly indefinite, and not just a case where we don't know the order? The answer lies in a clever mathematical tool known as a causal witness. Think of it as a special kind of measurement, designed to tell two different kinds of reality apart. It mathematically separates processes that have a definite causal order from those that exist in a superposition of orders. The logic is this. Any process with a definite causal structure, A before B, B before A, or even a random chance of either, must obey certain mathematical rules known as causal inequalities. All such processes exist inside a boundary defined by these rules. A causal witness is a measurement constructed to test this boundary. If the process being tested has any kind of definite causal order, the value measured by the witness will always be above a certain threshold, 0 or greater. However, if a process is truly causally indefinite, like in the quantum switch, measuring it with the correct causal witness will yield a negative value. A negative result is the quiet proof. It shows that the process could not have been produced by any combination of definite causal orders. It is a direct violation of the causal inequality. This is precisely what teams of physicists have now accomplished. In the 2017 experiment at the University of Vienna, the team led by Giulia Rubino and Philip Walther implemented a causal witness to test their quantum switch. When they analyzed the results, they found a value that was clearly negative, demonstrating with high statistical significance that the process inside their apparatus was incompatible with any definite causal order. It was the first experimental proof. Since then, other labs have replicated and refined these experiments. One challenge was that early experiments were device-dependent, meaning you had to trust your understanding of the lab equipment. The next frontier is a device-independent certification, which would provide proof just by looking at the raw data, without needing to know how the devices work internally. Theoretical work has shown this is possible, and recent experiments are providing powerful, device-independent evidence by violating causal inequalities under specific assumptions. These proofs rely on a sophisticated mathematical language called the process matrix formalism, developed by physicists like Oreshkov, Costa, and Bruckner. This framework describes quantum mechanics without assuming a background causal structure from the start. The causal witness is the tool that can experimentally read the process matrix and tell you which kind of reality you have. The success of these experiments transforms indefinite causal order from a theoretical curiosity into a documented feature of our universe. The evidence is in. The timeline is not as solid as it seems. This is the very edge of what we know. The science we're talking about is happening right now, with new discoveries quietly redrawing the map of reality. If this kind of calm exploration into the deepest laws of the universe helps you unwind, consider subscribing to the channel. We are on this journey together, and we release new explorations into the strange and beautiful world of science every week. The shape of a fluid past. So, what does it all mean? We have experimental proof that the order of events can be indefinite, and that a future measurement can define the causal nature of a past event. The implications of this ripple outwards, touching on the nature of time itself, the search for a theory of everything, and even the future of technology. First, we must reconsider our concept of time. We experience it as a universal, flowing river. But indefinite causal order suggests this river may be an illusion that appears at our large, classical scale. At the fundamental quantum level, there may be no single timeline. Instead of a line, reality might be better described as a network of events, where the links of before and after are themselves quantum properties that get established through interaction. The idea that time as we perceive it emerges from a deeper, timeless layer of reality has long been a speculative one. Now, for the first time, experimental results are giving this idea a quiet foothold in the real world. This leads directly to one of the greatest challenges in physics, quantum gravity. For a century, physics has been split between general relativity, which describes the large-scale universe of gravity and smooth spacetime, and quantum mechanics, which describes the small-scale world of particles and probabilities. Many theories of quantum gravity predict that at the tiniest possible scales, spacetime itself should break down into a chaotic, quantum foam, where definite causal order would lose its meaning. What is so remarkable about indefinite causal order experiments is that they may be giving us our first experimental glimpse into the physics of quantum gravity, right here on a laboratory tabletop. Beyond these deep questions, indefinite causal order also has surprising practical implications, especially for quantum computing. A quantum computer already gets its power by processing many possibilities at once. By putting the asterisk order of operations into a superposition, the quantum switch allows for new kinds of algorithms that can be more efficient for certain tasks. For instance, researchers have shown that a quantum switch could be used to send information through two completely noisy channels that should, by all other measures, have zero capacity to transmit anything. This suggests causally indefinite processes are a fundamentally new kind of resource in information theory, one we are only just beginning to understand. Finally, we are left with the philosophical impact. The idea that the future can define the past is provocative, but it reflects the strangeness we are confronting. It is not influence in the sense of a signal, but in the sense of definition. The future measurement provides the context that solidifies the reality of the past event. It forces us to let go of the idea that the past happened in one specific way, even if we didn't see it. Quantum mechanics suggests the past, like the present, can be a superposition of possibilities. The story of the universe isn't a single, fixed narrative. It's a collection of potential storylines, and our interactions with the universe, even our future ones, play a role in which storyline becomes real. We began with a simple idea: cause and effect, the unwavering sequence that builds our world. We saw how quantum mechanics first blurred this picture, replacing certainty with a quiet cloud of probability. We then journeyed into the heart of the quantum switch, a real device where before and after can exist at the same time. We learned about the causal witness, the mathematical tool that proves this is not a trick, but a genuine feature of the physical world. This is not science fiction. The experiments have been done. In laboratories across the world, Scientists are right now demonstrating that the firm boundary between past and future is not as firm as it seems. We live our lives on what feels like the solid ground of a fixed past. But science has revealed that beneath this ground, at the very foundations of reality, lies a quantum realm where the rules of time are different. In this world, there is not always an absolute before and an absolute after. There is a network of events, woven together by threads of quantum information that can loop in ways that defy our classical minds. The universe, it turns out, does not write its story in a straight line. It writes it in a language of possibilities, where the act of reading a page in the future can help determine what was written on a page in the past. And the most astonishing part of this entire story is that we, after so long, are finally learning how to read this strange and wondrous new language. Einstein's nightmare. The spooky glitch in reality. What if I told you there's a glitch in reality? A spooky, ghostly connection that lets two particles, separated by billions of miles, be instantly linked. A connection that seems to work faster than light, shattering the cosmic speed limit that underpins, well, everything we know about physics. It's a phenomenon so bizarre, so contrary to our gut feelings, that it seems to tear a hole in the very fabric of the universe. When the greatest mind of the 20th century, Albert Einstein, first bumped into this idea, he was horrified. He called it spookhafte Fernwerking, which perfectly translates to spooky action at a distance, and he flat out refused to believe it could be real. For him, it was a nightmare, a ghostly apparition haunting the elegant, orderly universe he had spent his life describing. He was convinced that this new, weird theory of quantum mechanics, where the idea came from, had to be missing something. There just had to be a deeper, more sensible explanation. But what if he was wrong? What if the nightmare was real? Today, we're going to journey into the heart of this quantum mystery. We'll explore the mind-bending experiments that took spooky action from a philosophical argument and proved that this ghostly link is very, very real. In doing so, these experiments uncovered a fundamental crack in our understanding of the universe, forcing us to question the very nature of space, time, and reality itself. This isn't just a physics story. It's a story about common sense unraveling and coming face to face with a universe that is far stranger and more interconnected than we ever dared to imagine. The Titan's disbelief. Einstein's perfect universe under threat. To get why this spooky connection bothered Einstein so much, you have to understand the man and the universe he had built. By the early 20th century, Einstein had single-handedly rewritten the laws of gravity and motion. His theories of special and general relativity were towering intellectual achievements, painting a picture of the cosmos that was both beautiful and, most importantly, predictable. At the very core of Einstein's worldview were two principles that felt like unshakable bedrock: locality and realism. First, locality. This is an idea that just feels like common sense. It says an object can only be directly affected by its immediate surroundings. If I want to push a book, I have to touch it. For the sun's gravity to hold the Earth in orbit, that influence has to travel across the 93 million miles between them. Nothing happens instantly. And, according to Einstein's own special theory of relativity, the absolute, unbreakable speed limit for any influence, any signal, any information, is the speed of light. That cosmic speed limit wasn't just a suggestion, it was the central pillar of his entire framework. So, the idea of an effect happening instantly across a huge distance? To him, that was a violation of causality, a slide into magical thinking. Second, realism. This is more philosophical, but just as intuitive. It's the belief that objects have definite, real properties, whether we're looking at them or not. The moon is still there, orbiting the Earth, even when you close your eyes. A coin you've flipped and covered with your hand is either heads or tails. You just don't know which one yet. Looking at it just reveals what was already there. To Einstein, the universe was a grand, deterministic machine. Its workings might be complex, but it was fundamentally knowable. As he famously quipped, he believed, God does not play dice with the universe. Reality, for Einstein, wasn't a game of chance. Then came quantum mechanics. This new theory, popping up in the 1920s, was a wild, statistical beast. It described the subatomic world not with the certainty of Einstein's equations, but with a fuzzy haze of probabilities. According to quantum mechanics, before you measure a particle, it doesn't have definite properties. An electron doesn't have a specific position. It exists in a superposition, a cloud of all its possible positions at once. It doesn't have a definite spin, a quantum property sort of like angular momentum. It's both spin up and spin down at the same time. The act of measurement, this new theory said, is what forces the particle to choose a state, collapsing its cloud of possibilities into one single reality. Einstein hated this. He couldn't accept a reality governed by chance, a reality that only becomes real when we decide to look at it. He was sure the quantum description was just incomplete. The particle, he argued, must have had a definite spin all along. We just didn't have the tools to know it. The quantum probabilities, he thought, weren't a reflection of reality, but a reflection of our own ignorance. This deep philosophical divide came to a head in 1935. Working with his colleagues Boris Podolsky and Nathan Rosen, Einstein cooked up a brilliant thought experiment to expose what he saw as the absurdity at the heart of quantum mechanics. It became known as the EPR paradox. It goes like this. Imagine a particle that decays into two smaller particles, particle A and particle B, which then fly off in opposite directions. Quantum mechanics lets these two particles be created in a special, connected state called entanglement. In this state, their properties are linked. For instance, if you set them up so their total spin is zero, then you know that if you measure particle A and find it has spin up, particle B, no matter how far away it is, must instantly have spin down. Here's where Einstein saw the paradox. Let's say we wait until particle A is on Earth, and particle B is on Mars. We measure the spin of particle A and find its spin up. Instantly, we know particle B on Mars is spin down. But how? According to the quantum rulebook, neither particle had a definite spin until we measured it. So when we measured particle A, did our action here on Earth instantaneously cause particle B, millions of miles away, to snap into the opposite state? That would need some kind of influence moving faster than light, a direct violation of Einstein's own theory. This was the spooky action at a distance he found so unbelievable. Einstein, Podolsky, and Rosen argued this was a logical contradiction that proved quantum mechanics had to be incomplete. The only sensible alternative, they said, was that the particles had definite spins from the moment they were created. They were like a pair of gloves. Imagine putting one left glove and one right glove into two separate boxes and shipping one to Mars. You don't know which is which, but the property of left or right-handedness is already set. When you open the box on Earth and find a left glove, you instantly know the one on Mars holds a right glove. No spooky action, no faster than light message. The information was there all along, just hidden from you. Einstein called these predetermined properties local hidden variables. He was certain they existed and that finding them would restore order, realism, and locality to the universe, proving that God, indeed, does not play dice. For decades, this was a philosophical standoff, a debate between two of physics' greatest minds, Einstein and his intellectual sparring partner, Niels Bohr, with no way to prove who was right. Was the universe locally real, as Einstein insisted? Or was it fundamentally strange and interconnected, as quantum mechanics suggested? The question cut to the very core of what reality is. And without an experiment to test it, it seemed doomed to remain a debate forever. The Copenhagen counter-argument, Bohr's world of uncertainty. Facing Einstein's relentless attack on quantum theory was the Danish physicist Niels Bohr. If Einstein was the champion of a deterministic, clockwork universe, Bohr was the chief architect and defender of the new, strange, and probabilistic quantum world. He was the patriarch of the Copenhagen interpretation, the main way of thinking about quantum mechanics that grew out of intense discussions in the city it's named for. Bohr's view of reality was radically different from Einstein's. Where Einstein saw solid, definite properties just waiting to be discovered, Bohr saw a world that was fundamentally fuzzy and uncertain until it was measured. For Bohr, the superposition wasn't a sign of our ignorance about a particle's true state, it was the particle's true state. The electron wasn't secretly in one specific place, it was genuinely spread out in a wave of probability. This led to a deeply unsettling conclusion about the role of the observer. In Einstein's classical world, an observer is a passive bystander, just recording what's already happening. But in Bohr's quantum world, the act of measurement is a dramatic, transformative event. It's the interaction between the measuring device and the quantum system that forces the fuzzy cloud of possibilities to collapse into a single concrete outcome. Before the measurement, there are only probabilities. After the measurement, there is a fact. Reality, in a very real sense, is created by the act of observing it. This philosophical clash defined the famous Bohr-Einstein debates, a series of arguments that raged for years. Einstein would constantly dream up clever new thought experiments, like the EPR paradox, to poke holes in the Copenhagen interpretation and show its logical absurdities. He tried to find ways to measure a particle's properties without disturbing it, to peek behind the curtain of quantum uncertainty and prove a definite reality was hiding there. Bohr, in response, would meticulously pick apart every one of Einstein's arguments. He showed, time and again, that within the rules of quantum mechanics itself, there was no getting around the fundamental uncertainty. When it came to the EPR paradox, Bohr's response was radical. He didn't deny the strange connection. He embraced it. He argued that it was a mistake to even think of the two entangled particles as separate, independent things, no matter how far apart they were. From the moment they were created, they formed a single, indivisible quantum system, described by a single, shared wave function. To Bohr, when you measure particle A on Earth, you aren't sending a spooky, faster-than-light signal to particle B on Mars. You're performing an action on the entire quantum system as a whole. Because they are fundamentally one thing, an observation on one part instantly gives you information about the other. The concept of locality, that things are only affected by their immediate surroundings, simply breaks down in the quantum realm. It's not that a signal is breaking the speed of light, it's that the two particles are so deeply interconnected that the idea of distance between them loses its normal meaning. This was a complete break from our intuitive picture of the world. It suggested the universe isn't a collection of separate objects, but a holistic web of relationships. For Einstein, this was philosophical madness. It was giving up on the scientific principles he held dearest. He felt that Bohr and his colleagues were so in love with their new theory that they were refusing to see its obvious holes. The idea of local hidden variables, that hidden information could explain the correlations without any spooky action, seemed not just plausible, but necessary for a sane description of the world. So, the battle lines were drawn. On one side, Einstein, pushing for a universe that is local and real. On the other, Bohr, defending a universe that is non-local and probabilistic. For nearly 30 years, that's where things stood. It was a clash of titans, a profound disagreement about the fundamental nature of existence. But it was just that, a disagreement. There seemed to be no experiment that could actually test these two opposing worldviews. To move forward, it would take a flash of insight from a physicist who dared to ask a question no one else had. What if we could design an experiment to tell the difference? The experimental gauntlet, putting reality to the test. For decades, the Bohr-Einstein debate was a stalemate. Then, in 1964, a physicist at CERN named John Stuart Bell had a breakthrough that changed everything. He was fascinated by the EPR paradox and wanted to drag it out of philosophy and into the real world of physical tests. Bell's genius was realizing that while Einstein's hidden variables and Bohr's quantum mechanics gave the same predictions in the simple EPR setup, a more subtle test might be able to pry them apart. His work, now known as Bell's theorem, did exactly that. He imagined our entangled particles, A and B, sent to two observers, Alice and Bob. But this time, let's not just measure their spin along one axis. Let's give Alice and Bob dials they can set to different angles before each measurement. Bell then did the math. He assumed Einstein was right, that each particle carried a set of hidden instructions that predetermined the outcome for any possible measurement. Working from this assumption of local realism, Bell derived a mathematical rule, now known as Bell's inequality. This inequality set a strict limit on how much correlation Alice and Bob could ever see between their measurements, on average. If reality was based on local hidden variables, the statistical correlation between their results could never exceed a certain value. It was a mathematical line in the sand. Then, Bell calculated what quantum mechanics would predict for the same experiment. And here's the kicker. Quantum mechanics predicted the correlations would be stronger than Bell's inequality allowed. It predicted a level of connection that was simply impossible in any universe governed by local, hidden instructions. Suddenly, the philosophical debate became a testable scientific question. We could finally settle the battle in the lab. The instructions were clear. Build an experiment, generate entangled particles, send them in opposite directions, measure their properties at different, randomly chosen angles, and look at the results. If the correlations obeyed Bell's inequality, Einstein was right. But if they violated it, then the universe was fundamentally, irreducibly, spooky. The first big tests began in the 1970s, but the definitive experiments were performed by a team led by French physicist Alain Aspect in the early 1980s. For this work, Aspect, along with John Clauser and Anton Zeilinger, would eventually be awarded the 2022 Nobel Prize in Physics for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Aspect's experiments were masterpieces of precision. His team built a device that generated pairs of entangled photons and sent them flying in opposite directions, about 6 meters to each side, to two measurement stations. At each station was a polarizer that could measure the photon's polarization, which is like its spin. Crucially, Aspect knew he had to close a potential flaw called the locality loophole. What if the two detectors were secretly talking to each other with some unknown, normal signal? To close this loophole, Aspect used ultra-fast switches that could change the angle of the polarizers while the photons were already in flight. The choice of measurement was made so late that there wasn't enough time for a signal, even at the speed of light, to get from one detector to the other and influence its outcome. The results were stunning and unambiguous. Time and time again, Aspect's experiments showed a clear violation of Bell's inequality. The correlations were exactly what quantum mechanics predicted and way stronger than any local hidden variable theory could explain. Einstein's common-sense idea of a locally real universe was wrong. The spooky connection was real. Even Aspect's work left a few tiny cracks for skeptics, like the detection loophole. Not every photon was detected. What if the ones being missed were conspiring to skew the results? It was a long shot, but it had to be closed. That final nail in the coffin came in 2015. Several teams, including one led by Ronald Hansen at Delft University of Technology, conducted loophole-free Bell tests. These experiments were technological marvels. The Delft experiment used entangled electron spins in two diamond crystals separated by 1.3 kilometers. They used super-efficient detectors and fast, random number generators to close both the detection and locality loopholes at the same time. Some experiments even used light from distant quasars, billions of light-years away, to determine the measurement settings, using a source of randomness so ancient there's no way it could have been influenced by the experiment itself. The verdict was unanimous and overwhelming. Every single one of these tests confirmed the predictions of quantum mechanics. They all showed a powerful violation of Bell's inequality. The case was closed. Nature, at its most fundamental level, is non-local. The spooky action at a distance isn't a flaw in the theory. It's a fundamental feature of our universe. The verdict and its consequences: living in a spooky universe. The proof of quantum entanglement is arguably one of the most profound discoveries in science history. It forces us to rethink our deepest gut feelings about the world. The universe, it turns out, doesn't operate like a collection of separate billiard balls. It behaves like a vast, interconnected web, where parts that seem separate can be linked in ways that defy our classical understanding of space. So what does this actually mean? Can we send messages faster than light? Build an instantaneous galactic telephone? The answer, maybe frustratingly, is no. And the reason shows another layer of quantum weirdness. While the connection between entangled particles is instantaneous, you can't use it to send useful information faster than light. Let's go back to Alice on Earth and Bob on Mars. Alice measures her particle and gets spin up. She instantly knows Bob's particle is spin down. But this doesn't help her send a message. The outcome of her measurement was completely random, a 50-50 shot. She couldn't force her particle into a spin up state to send a 1, or a spin down state to send a 0. Bob, on Mars, also sees a perfectly random result. He has no idea if his result is correlated with an observation by Alice or just a random quantum event. The only way for them to see the spooky correlation is to later get together and compare their notebooks. Bob would have to call Alice on a regular radio, traveling at the speed of light, and compare notes. The correlation is only revealed after they communicate in the old-fashioned, slower-than-light way. So, Einstein's cosmic speed limit for communication is safe. Relativity holds up. What has been shattered is the principle of local realism. The experiments proved you can't have both. You have to abandon at least one. Either influences can be instantaneous, violating locality, or the properties of objects aren't real until they are measured, violating realism. Standard quantum mechanics says we have to let go of a locally real universe. The implications are mind-bending. It suggests that at the deepest level, the universe isn't made of separate parts. The two entangled photons, even when separated by kilometers, aren't two separate things. They are one single quantum entity. The space between them just doesn't seem to matter in the way it does for us. This idea hints that our perception of a world made of distinct, separate objects might just be an illusion, an emergent property of a much deeper, more holistic reality. And this isn't just abstract philosophy anymore. This glitch in reality is now being used to create revolutionary new technologies. Quantum cryptography uses entanglement to create perfectly secure communication. If a spy tries to intercept a message, the act of measuring it disturbs the system in a way that immediately gives them away. Quantum computing promises to solve problems that are impossible for even today's most powerful supercomputers. By linking quantum bits, or qubits, together through entanglement, these computers can explore a vast number of potential solutions all at once. And then there's quantum teleportation. It's not like in Star Trek, we're not beaming people around. But we can use entanglement to teleport the exact quantum state of a particle onto another one far away. It's like faxing the soul of a particle, destroying the original in the process. This tech, once science fiction, is now a real building block for a future quantum internet. The research continues to push boundaries, exploring entanglement between different kinds of particles and even probing what it means for identical particles to be entangled. The rabbit hole just keeps getting deeper. The story of quantum entanglement is about a revolution that forced us to face the limits of our own intuition. It started with Albert Einstein, a titan of physics, who looked at the bizarre predictions of quantum theory and said, "No, that can't be right." His gut feeling, his deep belief in an orderly and sensible universe, made him dismiss the ghostly connection between particles as spooky action at a distance. He was sure there had to be a hidden layer to reality. But science isn't about gut feelings, it's about evidence. Through the brilliant theory of John Bell and the ingenious experiments of pioneers like Alain Aspect, we put reality itself on trial. We asked the universe a direct question. Are you the clockwork machine of Einstein's dreams, or the weird, interconnected web of Bohr's quantum world? The answer came back loud and clear. Reality is spooky. The glitch is real. Einstein, the man who reshaped our understanding of space and time, was wrong about this one. The experiments proved our universe is fundamentally non-local. It has a strange, instantaneous connection that links the fates of particles across vast distances, a connection that violates our deepest assumptions about cause and effect. Yet, in a beautiful twist of cosmic irony, this spooky glitch doesn't lead to chaos. It doesn't break the ultimate speed limit. Instead, it unlocks a deeper understanding of reality and opens the door to technologies that will redefine our future. It reveals a universe that is more subtle, more mysterious, and more wondrously interconnected than we ever knew. Einstein's nightmare turned out to be nature's reality. And we are just beginning to wake up to what that truly means. The next time you look up at the night sky, remember that the points of light you see aren't just isolated specks in the dark. They are all part of a single, vast quantum system, bound by invisible threads in a dance that spans the cosmos. The universe isn't just out there, it's connected. And that might be the most wonderful truth of all. If this journey into the spooky heart of reality bent your mind, make sure to subscribe and hit the bell icon so you don't miss our next exploration into the universe's biggest mysteries. And let me know in the comments, what aspect of the quantum world do you find the most mind-bending? Thanks for watching. Quantum physics just proved your choices can rewrite the past. There is a rhythm that underpins our world, a quiet and seemingly constant rule. Cause always comes before effect. A glass falls, and then it shatters. A match is lit, and then it burns. The flow of time feels like a gentle, forward-moving current, carrying us from a fixed past, through the present, and into a future of unrealized possibilities. This sequence is the foundation of our understanding, the basis for how we make sense of everything. But what if an experiment, repeated in labs across the world, seemed to show something else entirely? What if a choice made now could appear to alter an event that has already happened? This is not a story or a speculation, but the result of a real quantum experiment, one so unfamiliar that it seems to give our choices a role in shaping history. For years, this experiment has been presented as evidence of the impossible, suggesting that the future can influence the past and that time is not the one-way path we thought it was. Today, we will walk through this seemingly impossible result. We will look closely at the paradox it presents. And then, we will explore the quiet, profound, and ultimately satisfying truth the universe is showing us. The answer is not that causality is broken. The answer is something far more strange. The quiet rule of cause and effect. Before we enter the quantum world, it is helpful to ground ourselves in the one we experience every day. It is a world governed by causality. Think of your morning. An alarm sounded, and that caused you to wake. You felt hunger, and that caused you to prepare a meal. You poured coffee, and gravity caused it to fall into your cup. This order feels non-negotiable. The alarm cannot ring because you woke up. The hunger cannot arrive because you ate. Physicists call this the arrow of time, a direction that points relentlessly forward. The past is a landscape of events that have already occurred, causes that have rippled outward to form the present moment. The future is a realm of potential effects, waiting to be born from the actions we take right now. This principle is so fundamental, it is woven into the laws of classical physics. When an astronomer predicts the path of an asteroid, they use the laws of gravity, the cause, to calculate its future position, the effect. They can also reverse the calculation, using its current position to see where it must have been 100 years ago. The timeline is a chain of logic. Each link is forged by the one before it. If you were to see a shattered glass on the floor spontaneously reassemble and return to a table, you would question your senses. You would know, instinctively, that you had witnessed the impossible. In our world, effects do not choose their causes. The past is not open to revision. It is important to hold that feeling of certainty in your mind. Because we are about to enter a realm where that certainty is challenged. A realm where a particle's history appears to be decided by a choice that has not yet been made. To understand how such a question could even be asked, we first need to visit the origin of all quantum weirdness. A simple experiment with two slits. The double-slit experiment. The first unfamiliar shape. Imagine a barrier with two thin, parallel slits cut into it. On one side, a machine fires tiny particles, one by one. On the other, a screen records where each particle lands. This is the stage for one of the most unsettling experiments in physics. If you cover one slit and fire the particles, you get what you expect: a single band on the screen, just behind the open slit. The particles travel in a straight line and make their mark. If you open both slits, logic suggests you should get two bands, a simple combination of the two separate patterns. Each particle goes through either the left slit or the right. This was the accepted story for a long time. But in the early 20th century, scientists began to perform this experiment with things much smaller than paintballs. They used single photons, the fundamental particles of light. And it was here that reality began to show an unfamiliar shape. When they fired these photons one by one with both slits open, they did not get two bands. Instead, what emerged on the screen was a pattern of many stripes, a series of bright and dark regions. This is an interference pattern. And the only thing we know of that creates such a pattern is a wave. Think of ripples in a pond. If you drop two pebbles, the two sets of waves interfere. Where two crests meet, they create a larger wave. Where a crest meets a trough, they cancel out, leaving a calm spot. The pattern on the screen was undeniable. The single photon, which should be a particle, was behaving like a wave. It seemed to pass through both slits at the same time, interfere with itself, and then arrive at the screen. Physicists call this superposition. The photon does not choose a path, it exists as a cloud of possibilities all at once. This is where the experiment becomes even stranger. Baffled by this, the physicists decided to try and see which path the photon took. They placed a small detector next to one of the slits, a device that could report whether a photon passed through it. They wanted to force the universe to show its hand. And the universe did, but in a quiet, shocking way. The moment they turned on the detector to find out which path the photon took, the interference pattern vanished. In its place, two simple bands appeared, just as they would with particles. The very act of observing the photon's path forced it to choose a slit. It ceased to be a wave of potential and collapsed into a single particle with a definite history. This is the central mystery of quantum mechanics. Reality seems to shift depending on whether we are looking. The photon, somehow, seems to know it is being watched. This discovery led to a new, even more profound question. What if we could wait? What if we could let the photon pass the slits, complete its journey, and only after it has already landed, decide whether to find out which path it took? Could we still change its past? This is the thought experiment that led to the delayed choice. The ultimate mystery, the delayed choice quantum eraser. The core idea grew from the work of the physicist John Archibald Wheeler, who enjoyed pushing the boundaries of physics with mind-bending scenarios. He asked, what happens if we delay our choice to measure the path? How late can we wait? For decades, this remained a thought experiment. But in 1999, a team of scientists led by Marlin Scully helped bring a version of this impossible idea to life. The experiment they built is known as the delayed choice quantum eraser, and its results sparked a deep controversy about rewriting the past. The setup is intricate, so it helps to go through it carefully. First, scientists use a special crystal that, when hit by a single high-energy photon, splits it into two new, lower-energy photons. These two photons are entangled. This is a crucial concept. Entanglement means the two photons are now linked, part of a single quantum system. Whatever you learn about one instantly tells you something about its twin, no matter how far apart they are. Let's call them the signal photon and the idler photon. The signal photon's journey is short. It is sent toward a double-slit setup. After passing the slits, it travels to a detector, D0, which simply records where it lands. The path from the crystal to detector D0 is very short. The signal photon arrives and makes its mark quickly. Its journey is over. The idler photon's journey is much longer and more complex. It is sent on a winding path, and this is where the choice is made. This path eventually leads to a system of beam splitters and mirrors. The idler photon can end up at one of 4 different detectors. 2 of these detectors, D3 and D4, provide which path information. If an idler photon hits D3, the physicists know its signal twin went through slit A. If it hits D4, they know it went through slit B. The other 2 detectors, D1 and D2, are different. Before reaching them, the idler photon's path is scrambled in such a way that it becomes impossible to know which slit its twin went through. The which path information is effectively erased. So, we have a choice. Depending on where the idler photon lands, we either know the signal photon's path, D3, D4, or we erase that knowledge, D1, D2. Now for the mind-bending part. The path for the idler photon is much longer than the path for the signal photon. The signal photon hits detector D0 and its journey is finished long before its idler twin even reaches the apparatus that decides whether to keep or erase the path information. The signal photon's arrival is a past event. The choice about its path happens in what is, for the signal photon, the future. Here is the result that seems to break reality. The scientists run the experiment. At first, the pattern of dots from the signal photons at detector D0 looks like a random, scattered blob. But then, they begin sorting the data. They look only at the signal photons whose entangled idler twins were detected at D3 or D4, the ones where the path information was known. When they plot just those marks, they see 2 simple bands. A particle pattern. It is as if these signal photons knew their path would be measured in the future, so they behaved like particles in the past. Then, they do the opposite. They look only at the signal photons whose idler twins landed at D1 or D2, the ones where the path information was erased. When they plot those marks from D0, a stunning interference pattern emerges. A wave pattern. It is as if these photons knew their path information would be erased, so they behaved like a wave in the past. Let this sink in. An event that has already happened, a photon landing at D0, appears to change depending on a choice made later. It's like the photon's past behavior, particle or wave, is determined by a future measurement. How can this be? Did we just prove that time is a two-way street? This is the paradox that has fascinated physicists. But the resolution is even more elegant than the puzzle itself. The great revelation. Sorting the data. So, we stand at the edge of a logical cliff. The evidence seems to show a future event dictating a past reality. Is it time to discard everything we know about the universe? The answer is no. Our simple idea of causality is safe from paradox. But to understand why, we have to look closer at the subtle process at the heart of the experiment. The mind-bending patterns do not appear in real time. The illusion is created entirely by how we choose to sort the data after the experiment is over. Let's return to detector D0, where the signal photon arrives. What does an observer standing next to D0 actually see? They do not see an interference pattern one moment and two clumps the next. All the observer at D0 ever sees is a seemingly random, scattered cloud of dots. There is no visible pattern at all. Just noise. The magic happens later, in a computer that holds two lists of data. One list has the coordinates for every signal photon that landed at D0. The other has which detector, D1, D2, D3, or D4, each corresponding idler photon hit. Now, a scientist sits down and says, "Show me only the landing spots from D0 for the signal photons whose twins landed on detector D1, the eraser detector." The computer filters through millions of data points. And when it plots this small, carefully chosen subset, a beautiful interference pattern emerges. It was hidden inside the noisy blob all along. The future choice is not reaching back in time to change how the photon behaved. Instead, the total pattern seen at D0 is the sum of all possibilities, several different patterns all superimposed on top of each other, creating what looks like a featureless mess. We are not changing the past. We are simply sorting the present data into different piles. The interference pattern was always there, encoded in one subgroup of photons. The particle pattern was also always there, in another subgroup. Our delayed choice is simply the act of choosing which pile to look at. Perhaps an analogy is useful. Imagine hosting two conferences at once in the same hall, one for artists, one for accountants. At the end of the day, a guard at the front door is asked, "What kind of people came today?" The guard would just shrug and say, "All sorts." It was just a big, random crowd. They see no pattern. But later, you go through the registration lists. You say, "Let's plot on a map where only the artists live." You might see they're clustered downtown. Then you plot where only the accountants live, and you see they're clustered in the suburbs. Did your choice to sort the list by profession change where these people lived? Of course not. The patterns were always there. You just could not see them until you used other information to separate the jumbled crowd into meaningful groups. This is what the delayed choice quantum eraser does. Detector D0 is the guard seeing a random crowd. The idler detectors are the registration lists. And the scientist sorting the data is revealing hidden patterns that existed all along. You only see a pattern when you choose to look at an incomplete subset of the data. What this means for reality, and what it doesn't. So, causality, in the sense of creating paradoxes, is saved. You cannot use this experiment to send winning lottery numbers to your past self. To know which pattern to look for at detector D0, you have to wait for the information from the idler detectors. That information must travel through normal means, at or below the speed of light. By the time you have the information needed to decode the past, that moment is long gone. But if the experiment doesn't break causality, what is its profound lesson? The true lesson of the quantum eraser is not that the universe is illogical, but that our classical, everyday intuition is incomplete. It teaches us that quantum objects do not have definite properties like being a particle or being a wave before we measure them. They exist in a state of pure potential, a mathematical abstraction that contains all possibilities at once. More importantly, it redefines what a measurement even is. The measurement is not just the signal photon hitting detector D0. It is the entire experimental apparatus. The signal photon cannot be described independently from its entangled twin. What we learn from the idler photon doesn't change the signal photon's past. It helps define what information we are allowed to have about the system as a whole. If we set up the experiment to gain which path, information, we are asking the universe a particle-like question. And it gives a particle-like answer. If we set up the experiment to erase that information, we are asking a wave-like question. And it gives a wave-like answer. The experiment proves that the past of a quantum particle is not a fixed, single story. It is more like a book with multiple draft versions superimposed on top of each other. The measurement we choose to make in the present determines which draft of the past we are allowed to read. We are not rewriting the book. We are just choosing which chapter to open. And while this specific setup doesn't create paradoxes, it has opened a serious and ongoing debate among physicists about whether some form of backward-in-time influence, or retrocausality, might be a real and fundamental feature of our universe, a way of making sense of quantum mechanics without some of its other strange implications. The story is not finished. The question defines the answer. We began this journey with a startling idea that a choice made today could alter yesterday. We navigated one of the most intricate experiments in modern physics, one that seemed to capture this impossible act. And then, we found the truth was not that the past was being rewritten, but that our understanding of what the past is was being redefined. The illusion of a paradox was a ghost, born from the way we sort information in the present. The real revelation was that hidden within a seemingly random canvas were multiple, overlapping realities that could only be seen when we knew what to look for. The delayed choice quantum eraser does not break the law of cause and effect in a way that would let us change our own history. Instead, it exposes the limits of our simple, classical ideas. It forces us to accept a world where the properties of things are not static facts waiting to be discovered, but emerge from the way we interact with them. So, while your choices do not rewrite a fixed past, they play a profound role. They define the very questions you are allowed to ask of reality. And in the quiet and beautiful world of quantum mechanics, the question you ask does not just reveal an answer, it helps bring that answer into being. The universe is not a film we are passively watching. It is an interactive story. The past may not be a variable we can change, but our knowledge of it is, and the act of choosing what to know shapes the reality we experience. Why throwing an apple into a black hole breaks reality? Imagine a place in the universe where something could be truly erased. A place where you could take an object as simple as an apple, let it go, and have its existence removed from the fabric of reality itself. According to our deepest understanding of the world, such a place should not be possible. And yet, this is precisely what seems to occur when anything crosses the edge of a black hole. This quiet act creates a profound contradiction, a question in physics that compels us to ask if information can be lost forever, or if something far stranger is at work. The journey we are on is not just about a piece of fruit and a cosmic object. It is a journey to the very limits of what we know, to a place where our two great descriptions of the universe, general relativity and quantum mechanics, arrive at different answers. This is the story of the black hole information paradox, a puzzle so deep that finding its solution may mean rewriting the rules of reality itself. To understand this quiet crisis, we must first build our universe, beginning with two seemingly simple questions. What is a black hole, and what, in the language of physics, is information? The setup, building the arena. First, the black hole. It is helpful to set aside the image of a cosmic vacuum cleaner. A black hole is more like a place where the fabric of spacetime has been stretched to its breaking point. It is what remains when a truly massive star exhausts its fuel and can no longer hold itself up against its own gravity. Einstein's theory of general relativity, our guide to gravity, space, and time, tells us that if enough mass is concentrated in a small enough volume, the gravitational pull becomes so absolute that spacetime curves inward infinitely, creating a point of immeasurable density, a singularity. Around this singularity lies a boundary of no return, a one-way door called the event horizon. This is not a surface one could touch. It is a location in space, defined only by gravity. Once something crosses it, the pull is so strong that escape would require moving faster than the speed of light. And since nothing can travel faster than light, nothing that enters can ever leave. Everything that passes the event horizon is drawn toward the singularity, its journey sealed by the laws of gravity. Causality becomes a one-way street. For a long time, this was our understanding of a black hole. It was a simple object. So simple, in fact, that physicists described it with what they called the no-hair theorem. This principle states that a settled black hole can be described by only three external properties: its mass, its electric charge, and its rotation. That is all. Every other intricate detail of whatever fell inside, be it a star, a spacecraft, or an apple, is lost from view. The black hole has no hair, no features to tell you what it consumed. If you were to throw a crisp, red apple into a black hole, its mass would increase by a small amount. If you were to throw in a bruised, green apple of the exact same mass, the final state of the black hole would be identical. From the outside, there is no way to distinguish between the two events. General relativity says the black hole simply forgets. But this is where the story grows more complex, because the universe, according to our other great theory, is not permitted to forget. This brings us to our second concept: information. In physics, information is more than just data. It is the fundamental identity of every particle in the universe. It is the universe's blueprint, containing the properties that make each particle unique: its position, its velocity, its quantum state. A core principle of quantum mechanics, a law as certain as gravity, is that this information can never be truly destroyed. This rule is called unitarity. Imagine you burn a book. To our eyes, the story is gone. But in a physics sense, it is not. The information that once formed the book is now encoded in the arrangement of the smoke, the ash, the heat, and the light from the fire. It is scrambled, practically impossible for us to reconstruct, but it all still exists. If you could, in principle, gather every single particle released by the fire and trace its journey backward, you could perfectly restore the book. The universe, at its most fundamental level, remembers. The present state of the cosmos perfectly determines its past and its future. Information is conserved. And here, we have our arena. On one side stands Einstein's general relativity, which describes black holes as simple, information-devouring objects with no hair. They consume our apple and remember nothing but its mass. On the other side is quantum mechanics, which insists that the unique information of that apple, the quantum state of every one of its atoms, must be preserved. For a time, physicists could accept this quiet disagreement. The information was trapped, yes, but not destroyed. It was simply inside. One could imagine it was stored safely in the singularity, locked away from the rest of the universe. The laws of physics remained whole, even if one of them was hidden behind an impassable wall. But in 1974, Stephen Hawking entered the conversation, and with a single, remarkable calculation, he showed that this quiet disagreement was, in fact, a deep contradiction. He revealed that black holes are not eternal prisons. They evaporate. The confrontation, a deeper question. Stephen Hawking was not trying to break physics. He was trying to connect it. He wanted to understand what would happen if the rules of quantum mechanics were applied to the intensely curved spacetime just outside a black hole's event horizon. What he discovered changed our view of the cosmos. To understand Hawking's finding, we must look closer at what we call empty space. According to quantum field theory, the vacuum is not truly empty. It is a quiet, constant flicker of energy. In this space, pairs of virtual particles and their antimatter counterparts are continually emerging, borrowing a small amount of energy from the universe. Almost instantly, they meet, annihilate, and repay their energy debt. They exist for such a brief moment they are like ghosts, leaving no lasting trace on the world. But what happens if one of these pairs appears precisely at the edge of an event horizon? Imagine a particle and its antiparticle coming into existence there. In the extreme gravitational environment, one might be pulled into the black hole while the other escapes into space. The particle that escapes no longer has a partner. It cannot simply vanish. It becomes a real particle, radiating away from the black hole. To a distant observer, it appears as though the black hole is slowly glowing. This is Hawking radiation, but there is a cost. For that virtual particle to become real, it needs energy. It draws this energy from the only source available, the black hole itself. The particle that falls in can be thought of as carrying negative energy, which, when subtracted from the black hole, reduces its total mass. Because E equals mc squared, a loss of energy is a loss of mass. Each particle of Hawking radiation carries away a tiny fragment of the black hole. This process is incredibly slow. For a black hole the mass of our Sun, it would take far longer than the current age of the universe to lose even a small fraction of its mass. But given an almost unimaginable amount of time, every black hole will radiate away its entire being, disappearing in a final, gentle flash of energy. And here, a profound question settles. This is where the paradox takes hold. Hawking's calculations revealed something deeply unsettling about this radiation. It is thermal. This means it is random, like the uniform warmth from a piece of hot coal. The properties of the radiation depend only on the black hole's mass, charge, and spin. It carries no other information. It does not matter if the black hole was formed from a star, a fleet of spacecraft, or trillions of apples. As it evaporates, the radiation it emits is entirely featureless. So, when the black hole is completely gone, what has happened to the information about the apple we threw in? It cannot be in the black hole because the black hole no longer exists. It cannot be in the Hawking radiation because that radiation is thermal and random, holding no memory of what fell inside. It appears to have vanished. The unique quantum blueprint of our apple seems to have been deleted from the universe. This is the black hole information paradox. It is a quiet, deep disagreement between our two most successful descriptions of the world. General relativity, through the no-hair theorem, suggests the black hole forgets. Quantum mechanics, through the principle of unitarity, insists that information can never be lost. Hawking's discovery of evaporation forces a choice. If a black hole evaporates and the information disappears, then a fundamental principle of quantum mechanics is wrong. The implications are difficult to overstate. If information can be destroyed, the connection between past and future is broken. If one cannot, even in principle, reconstruct the past from the present, the universe loses its deep predictability. Physics as we know it would be fundamentally altered. Hawking himself initially believed this was the answer. He famously made a bet with his colleague John Preskill, suggesting that information was truly lost. It was a conclusion so unsettling that physicists have spent nearly 50 years trying to find another way, a search that has produced some of the most remarkable ideas in all of science. The exploration, escape from nothingness. The paradox left physicists with an uncomfortable choice. Either a cherished theory was incomplete, or something truly strange was happening at the edge of a black hole. The scientific community could not simply accept that the universe had a way to erase the past. The search to resolve the paradox became a search for a hidden mechanism, something that would allow the apple's story to survive. This search has led to ideas that stretch the boundaries of what seems possible. Possibility 1. The information is hidden in the radiation. The most conservative path was to suggest that Hawking's original calculation was not the full story. Perhaps the radiation is not perfectly thermal. Maybe there are subtle, quantum-level connections between the outgoing particles that secretly carry the information away. Imagine the apple's information is like a message written in invisible ink. The radiation appears random, but a hidden pattern is there, waiting to be understood. Physicist Don Page was an important voice in this line of thought. He argued that after a certain point, now known as the Page time, when about half the black hole has evaporated, the information must begin to come out. The randomness or entropy of the radiation could not increase forever. It would have to peak and then decline as the information was slowly released. This predicted pattern is now known as the Page curve. The problem, for decades, was that no one could find a mechanism that would allow these subtle patterns to emerge. Information cannot simply pass through the event horizon. And you cannot have the information existing both inside the black hole and outside in the radiation simultaneously. This would violate another core quantum rule, the no-cloning theorem, which states that you cannot make a perfect, independent copy of an unknown quantum state. This path, for a long time, seemed to lead to a quiet dead end. Possibility 2. The firewall. If the information must get out, but it cannot be cloned and cannot escape from inside, then perhaps it never truly gets inside at all. This thought led to one of the most debated ideas in modern physics, the firewall. Proposed in 2012, this theory suggests that the event horizon is not the calm, unremarkable place that Einstein's theory describes. According to relativity, an observer falling into a black hole should feel nothing special as they cross the horizon. The firewall concept sets this picture aside. It argues that to preserve information, the event horizon must be a violent, high-energy boundary. When our apple reaches the horizon, it does not pass through. It collides with this wall of fire and is instantly incinerated. Its information is immediately absorbed and encoded, ready to be radiated back out as Hawking radiation. This solves the information paradox directly. The information is never lost because it never enters the region from which it cannot escape. But this solution comes at a great cost. It appears to violate Einstein's general theory of relativity. The principle of a smooth, continuous spacetime breaks down at the horizon. For many physicists, this was too high a price to pay. It seemed to trade one paradox for another. Possibility 3. The holographic principle and fuzzballs. What if the problem lies in our understanding of space itself? This is where an idea that feels closer to philosophy than physics enters the story: the holographic principle. First proposed by Gerard T. Hooft and later developed by Leonard Susskind, this principle suggests that our three-dimensional reality might be a projection of information stored on a distant, two-dimensional surface. Much like a hologram on a bank card stores 3D information on a 2D film, the information of our universe could be encoded on an outer boundary. Applied to a black hole, this idea is transformative. It suggests the information of our apple does not fall into the 3D black hole. Instead, its information is encoded on the 2D surface of the event horizon itself. From our perspective, we see the apple fall in, but in this holographic description, its essence never crosses the boundary. It remains as a complex pattern on the horizon. As the black hole evaporates, this surface information can then be subtly imprinted onto the outgoing Hawking radiation. String theory, one of our leading candidates for a theory of everything, offers a possible physical picture for this. In some of these models, black holes are not a singularity with an empty horizon. They're fuzzballs, impossibly dense, tangled balls of fundamental strains. In this view, there is no sharp event horizon and no singularity. The object has a physical, if fuzzy, surface. When the apple makes contact with this fuzzball, its information is absorbed into the complex vibrations of the strains. This information is then slowly re-emitted in the radiation, which in this model is not perfectly thermal. Both ideas provide elegant ways for information to be preserved. But for a long time, they remained largely theoretical, without a clear mathematical mechanism to show that the information truly gets out in a way that would produce the page curve. This journey to the edge of reality is complex, and we're exploring ideas that challenge our deepest intuitions. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. Your support helps us continue to investigate these quiet mysteries, one question at a time. The breakthrough, islands and wormholes. For nearly 2 decades, the conversation continued. Then, in 2019, a series of profound calculations offered a new path forward, one that appears to reconcile Einstein and quantum mechanics without firewalls. The solution came from a new way of calculating information in systems with gravity, and it involves 2 beautifully strange concepts: quantum extremal surfaces and islands. To understand this breakthrough, we must return to the Hawking radiation. The particle that escapes the black hole and the particle that falls in are entangled. This is a fundamental quantum connection. As the black hole evaporates, the cloud of outgoing radiation becomes more and more entangled with the particles inside the black hole. The new calculations, which built upon the holographic principle, instructed physicists to take a counterintuitive step. When calculating the information content of the Hawking radiation far from the black hole, they found they also had to include a region inside the black hole. This region is called an island. Think of it this way: the cloud of Hawking radiation outside the black hole is one part of a system. The island is a portion of the black hole's interior that is so deeply entangled with the radiation that, from an information perspective, it behaves as if it is part of the radiation system. Early in the black hole's life, there is no island. The randomness of the radiation grows, just as Hawking predicted. But at the page time, the halfway point of evaporation, an island suddenly appears in the calculation. When the physicists included this island, the total information content of the radiation suddenly began to drop. The result perfectly matched the page curve that Don Page had predicted decades earlier. This was a moment of profound clarity. It showed, within these specific models, how information could be preserved. But how does the information get from the island inside the black hole to the radiation outside? The answer may be even more remarkable: wormholes. There is a conjecture in physics known as ER equals EPR. Proposed by Leonard Susskind and Juan Maldacena, it suggests that 2 entangled particles, EPR, are equivalent to being connected by a microscopic wormhole, or an Einstein-Rosen bridge, ER. In this view, entanglement and wormholes are 2 descriptions of the same reality. In the context of the information paradox, this means the deep entanglement between the radiation outside and the island inside creates a network of microscopic wormholes connecting them. The information from the apple, held within the island, does not need to break through the event horizon. It can tunnel through these spacetime wormholes directly to the outgoing radiation. The information does not need to be cloned because the island and the radiation are not truly separate. They are 2 parts of a single system, connected by these quantum shortcuts. This solution is deeply elegant. It does not require a firewall, which preserves Einstein's theory of a smooth spacetime. It preserves quantum unitarity, which saves quantum mechanics. It seems to emerge naturally from applying the holographic principle to our understanding of quantum entanglement. It suggests that gravity itself provides the mechanism for information to escape. The paradox, which once seemed to point to a flaw in our laws, was now showing the way toward how quantum gravity might work. It hinted that spacetime itself may not be fundamental, but is instead built from the geometry of quantum entanglement. So, what happens when we throw an apple into a black hole? Does it break reality? The answer, it seems, is no. But in avoiding that break, we have been led to a reality that is far stranger and more interconnected than we had imagined. The story of the apple is not deleted. It falls toward the event horizon, and from our perspective, appears to vanish. But its fundamental information is not lost in a singularity. Instead, it is encoded. For the first half of the black hole's life, it is stored in a way we cannot access, entangled with the fabric of the black hole itself. Then, as the black hole evaporates past its halfway point, a connection forms. A region deep inside, an island, containing the apple's information, becomes fundamentally tied to the radiation streaming away. Through a web of microscopic wormholes woven by quantum entanglement, that information tunnels out. It emerges scrambled, woven into the subtle chorus of the outgoing particles, but it is all there. Given enough time and power, we could, in principle, reconstruct the story of our apple. The universe, it turns out, remembers. Information is preserved. The black hole information paradox is not yet fully solved. These new ideas are based on calculations in simplified universes and have yet to be translated into a full theory of quantum gravity for our own. But the path toward a solution is clearer. The paradox that Stephen Hawking revealed to the world has served its purpose. It was not a mistake in the laws of physics. It was a signpost, a quiet guide pointing us toward a deeper truth. It has forced us to reconsider the nature of space, time, and information, and has revealed that the fabric of our cosmos may be stitched together by the threads of quantum entanglement. The simple act of tossing an apple into a black hole does not break reality, it illuminates it. Physics found the edge of the universe. We move through the world with a quiet faith in how it works. A cause is followed by an effect. Things have a place, and they exist in a moment. But there is a scale, a realm so deeply small that it makes a single atom seem as vast as a galaxy, where this quiet faith is gently tested. There, all of our familiar rules begin to dissolve. Physicists, in their patient search for a complete story of the universe, have journeyed to the smallest imaginable frontier, only to find a kind of horizon. A boundary where the laws of physics, the very language we use to describe existence, no longer seem to form coherent sentences. This is not simply a limit of our tools. It appears to be a fundamental feature woven into the fabric of the cosmos itself. It is a place so unfamiliar, so unlike our own, that it challenges the very meaning of space, time, and being. What happens when you try to look past this edge? The universe, it seems, has an answer. And it's an answer that redefines what we thought we knew about the world around us. We are not just talking about something difficult to measure. We are talking about a place where our understanding of reality itself seems to come to a quiet end. The smooth, predictable universe. For most of human history, the universe seemed a predictable, well-ordered place. The sun rose and set. An object, when released, would always fall. The world was governed by a set of rules that felt consistent and dependable. This was the world described by classical physics, a beautiful picture of reality painted by figures like Isaac Newton. In this view, space was a fixed and unchanging stage, an infinite three-dimensional grid. Time was a universal river, flowing at the same rate for everyone, everywhere. On this stage, the movements of objects could be described by precise, deterministic laws. If you knew the position and momentum of everything, you could, in theory, calculate the entire future and reconstruct the entire past. It was a clockwork universe, wound up and ticking along with a kind of mathematical grace. Then, at the start of the 20th century, Albert Einstein offered a profound shift in perspective. He showed that space and time were not separate things at all, but were woven together into a single, dynamic entity, spacetime. This fabric of spacetime was not a rigid stage, it was a flexible canvas. Massive objects like stars and planets did not pull on each other with a mysterious force. Instead, they gently warped the geometry of spacetime around them. Gravity, Einstein showed us, was simply the shape of this cosmic fabric. A planet orbiting a star is just following a straight path through curved space, like a marble rolling along the gentle slope created by a heavy ball on a stretched sheet. Even in this new and unfamiliar vision of reality, one thing remained: smoothness. Einstein's spacetime was a continuous, unbroken surface. You could imagine zooming in forever, and you would always find more spacetime, smooth and well-behaved. The laws of general relativity worked beautifully, from the scale of falling apples to the grand, silent dance of galaxies. It seemed that we had finally grasped the fundamental operating system of the cosmos. The universe was still a place of order, just a more complex and elegant order than we had previously imagined. We had mapped the large-scale structure of reality, and it was continuous and, most importantly, knowable. But this serene, geometric picture was about to find its limit. Because while Einstein was looking up at the stars, another group of physicists was looking down, into the heart of the atom, and the world they were discovering was anything but smooth or predictable. They were about to find the jagged, uncertain edge of reality that existed just beneath Einstein's calm cosmic ocean. The quantum leap downward. As physicists in the early 20th century began to explore the atom, they might have expected to find a miniature solar system, with electrons orbiting a nucleus like tiny planets. What they found instead was something else entirely. They found a world that did not follow any classical intuition, a world governed by the quiet and counterintuitive rules of quantum mechanics. This was not a world of definite positions and predictable paths. It was a world of probabilities and uncertainties. An electron wasn't a tiny ball. It was more like a cloud of possibility, existing in a superposition of many states at once, until the act of observation appeared to prompt it to choose. The foundation of this new reality was Werner Heisenberg's uncertainty principle. In our everyday world, you can know everything about an object at the same time. You can know its exact position and its exact momentum. But in the quantum realm, this is not possible. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This is not a limitation of our instruments. It appears to be a fundamental property of nature. The very act of observing reality seems to change it. This principle introduced a kind of fundamental fuzziness, an inherent blurriness, into the heart of existence. This quantum world was also a place of constant, subtle activity. Even in what we would think of as a perfect vacuum, a space empty of all matter and energy, there is a quiet hum of activity. Because of the relationship between energy and time in the uncertainty principle, particles can spontaneously come into existence from nothing, borrowing a tiny amount of energy from the vacuum, as long as they return it almost instantly. These virtual particles appear and disappear in pairs, a particle and its antimatter counterpart, existing for the briefest of moments before vanishing. The vacuum, it turns out, is not empty. It is a simmering, bubbling sea of transient existence. For many years, the two great pillars of modern physics, Einstein's general relativity and quantum mechanics, existed in a kind of peaceful separation. Relativity described the vast, smooth, cosmic scale of stars and galaxies, a universe governed by the elegant geometry of gravity. Quantum mechanics described the tiny, probabilistic scale of atoms and particles, a world of uncertainty. For the most part, they each kept to their own domain. The gravitational pull of a single atom is too small to matter, and the quantum weirdness of a planet is averaged out to nothing. But physicists knew this separation could not be the final story. There had to be a deeper theory, a quantum gravity, that could unite these two descriptions of reality. To find it, they would need to push both theories to their absolute extremes, into a domain where gravity becomes intensely strong and scales become incredibly small. They would have to journey to the Planck scale. Reaching the wall, the Planck scale. The journey to the bottom of reality has a final destination. It's a place not defined by location, but by the fundamental constants of nature. In the late 19th century, the physicist Max Planck, while working on a different problem entirely, noticed something curious. He realized that by combining three of the universe's most fundamental constants, the speed of light, c, the gravitational constant, g, and his own Planck's constant, h, he could create a set of natural units. These were not arbitrary human inventions like the meter or the second. They seemed to be quantities written into the source code of the cosmos. These units define what we now call the Planck scale. The most famous is the Planck length, which is 1.6 times 10 to the minus 35 meters. This number is so small it's difficult to find a good analogy. If you were to scale up a single atom to the size of the entire known universe, the Planck length would be about the height of a tree. It represents the shortest distance that seems to have any meaning. Then there is the Planck time, which is the time it takes light to travel one Planck length. It's a flicker of about 10 to the power of minus 44 seconds, a duration so brief that a single second is closer to the age of the universe than it is to 1 unit of Planck time. Finally, there's the Planck energy, an immense amount of energy for a single particle, measured in billions of joules. At first, these units were seen as a mathematical curiosity, a convenience for physicists. But as the 20th century unfolded, their profound significance became clear. The Planck scale isn't just a set of tiny measurements. It is the boundary where our current understanding of physics seems to break down. It is the scale where the powerful gravitational forces described by general relativity meet the uncertain, probabilistic world of quantum mechanics. It's the arena where quantum gravity is thought to be the only story. And what happens in that arena is stranger than anyone imagined. This is the edge of the known, not in distance but in scale. It is the floor of reality, the point beyond which the very concepts of space and time no longer seem to have the meanings we give them. It is a threshold, and trying to understand what lies beyond it reveals that the smooth, continuous fabric of spacetime we take for granted might just be an illusion. The foaming, jittering reality. So, what happens when we zoom into the fabric of spacetime, down past galaxies, stars, atoms, and their nuclei, all the way down to the Planck length? The serene, gently curving sheet of Einstein's relativity seems to vanish. What we might find instead is a chaotic, subtly shifting landscape. The physicist John Wheeler, in 1955, gave this idea a name: quantum foam. Imagine looking at the surface of a calm ocean from a great height. It appears smooth, flat, and tranquil. As you descend, you begin to see details: gentle swells, then waves, then choppy whitecaps. If you could get down to the molecular level, you would see a frenzy of H2O molecules in constant, energetic motion. Spacetime, at the Planck scale, is thought to be much the same. The smooth geometry we perceive is just a large-scale average. Down at its most fundamental level, spacetime might not be smooth at all. It could be a foamy, jittery place, constantly fluctuating in a quiet, chaotic dance. Why would this happen? It seems to be a direct consequence of the uncertainty principle applied to spacetime itself. Just as there is an uncertainty relationship between a particle's position and its momentum, there is one between energy and time. This is what allows virtual particles to briefly emerge from the vacuum. At everyday scales, the energy of these particles is minuscule. But as we consider smaller and smaller regions of space over shorter and shorter intervals of time, the uncertainty principle allows for larger and larger fluctuations in energy. At the Planck scale, these energy fluctuations become enormous. The energy spikes are so immense, and packed into such a tiny space, that they begin to have a dramatic effect on spacetime itself. According to Einstein's theory, energy curves spacetime. So these huge, fleeting bursts of energy would warp and twist the fabric of reality on an unimaginable scale. Spacetime itself would begin to boil. Tiny, tangled knots of geometry, miniature wormholes, and complex shapes might bubble up and vanish in a single Planck time. The geometry of space and the flow of time would become indefinite, fluctuating in a foam-like way. Within this foam, the most extreme objects in the universe could make a brief appearance: virtual black holes. The energy fluctuations might become so concentrated that they spontaneously collapse into microscopic black holes, with a mass of 1 Planck mass and a radius of 1 Planck length. But these would not be the stable, galaxy-sized objects we know from astronomy. Governed by the uncertainty principle, they would be ephemeral. They would wink into existence for a mere Planck time before instantly evaporating back into the vacuum in a tiny puff of Hawking radiation. Spacetime at its most fundamental level might not be a static backdrop, but a seething soup of virtual black holes popping in and out of existence everywhere. This is the possible nature of the vacuum, a chaotic, bubbling foam where the distinction between space, time, and matter becomes blurry. It sets the stage for an even more profound idea: the quiet collapse of cause and effect itself. The end of cause and effect. In our world, causality is a fundamental rule. A happens, and then B happens because of A. A glass falls, and then it shatters. The word, then, is important. The effect does not come before the cause. This simple, linear progression of events is the foundation of logic, of science, and of our ability to make sense of the universe. But at the Planck scale, this foundation begins to feel less solid. The universe, it seems, has a built-in feature that prevents us from ever observing a cause leading to an effect at this most fundamental level. To understand why, we can consider a thought experiment. How would you observe something at the Planck length? In physics, to see something small, you need to probe it with something that has a very short wavelength. And according to quantum mechanics, a shorter wavelength corresponds to higher energy. To see an atom, you need a particle with more energy than visible light. To see a proton, you need even more. So, to resolve an object as small as the Planck length, you would need a probe, a photon, for example, with an unimaginable amount of energy. You would need to pack the Planck energy into a volume the size of the Planck length. And this is where the universe presents a quiet paradox. What happens when you pack an enormous amount of energy, or mass, thanks to E equals mc squared, into an incredibly tiny volume of space? You create a black hole. The very act of trying to observe the Planck scale with enough precision would create a microscopic black hole. Your probe, the photon carrying the information you wanted to measure, would become trapped inside. The information about the event you were trying to see would be swallowed, hidden behind an event horizon. You could not get it back. The experiment would be undone by the very act of performing it. What if you tried to see more clearly by using an even more energetic photon? This would only make the problem worse. According to general relativity, the more mass or energy you add to a black hole, the larger its event horizon becomes. So, as you increase the energy of your probe to get a better look, the black hole you create simply gets bigger, swallowing an even larger region of space and hiding even more information. It's like trying to illuminate a tiny detail, but the more light you shine on it, the bigger the shadow it casts. This does not appear to be a technological hurdle we can one day overcome. It seems to be a fundamental limit imposed by the laws of physics themselves. At the Planck scale, the concept of causality, of one event causing another in a distinct sequence, becomes difficult to define. You cannot establish what caused what, because you cannot even observe the events without creating a black hole that erases the evidence. It's as if the universe has a fundamental privacy, a quiet veil at the bottom of reality. The chain of cause and effect is broken because the links of the chain are hidden from view, permanently and in principle. Physics loses some of its predictive power, because the idea of a sequence of events dissolves into a probabilistic fog behind an impenetrable wall. The ultimate uncertainty, Heisenberg's uncertainty principle was already a significant departure from classical physics. The idea that you couldn't simultaneously know a particle's exact position and momentum introduced a fundamental fuzziness to reality. But even in the strange world of quantum mechanics, one thing was often taken for granted: spacetime itself. Particles might be fuzzy, but the stage on which they moved, the coordinates of space and time, was solid. An event happened at a particular place and at a particular time. At the Planck scale, even this last bit of certainty may dissolve. As theorists have tried to combine gravity with quantum mechanics, some have proposed an even more profound form of uncertainty, sometimes called the generalized uncertainty principle. This idea suggests that you cannot measure position with perfect precision because, as we have seen, trying to do so creates a black hole. This implies there may be a fundamental minimum length. But the implications go even deeper. Some theories of quantum gravity propose that it's not just our measurement of spacetime that's uncertain. The coordinates of spacetime themselves may become fundamentally uncertain. What does this mean? It means that at the Planck scale, a point in space, or a moment in time, may no longer be a well-defined concept. Just as a quantum particle can exist in a superposition of multiple locations, an event at the Planck scale might exist in a superposition of multiple places and multiple times. The very coordinates, x, y, z, t, that we use to map out reality could become fuzzy, quantum mechanical concepts themselves. Space might no longer be a collection of definite points, but a probabilistic cloud. Time may no longer be a steady river, but a jittery, uncertain sequence. This gently challenges our most basic assumptions. Nearly every statement we make about the physical world assumes a definite spacetime. The cat is on the mat assumes a where and a when. But if the coordinates of spacetime are themselves uncertain, then the very concepts of where and when begin to fade. An event might not happen at a specific location, but in a fuzzy quantum superposition of locations. The relationship between two events becomes tangled, not just because it's hard to see, but because the very notions of before and after, here and there, no longer apply in a clear way. This leads to the idea that spacetime itself might be discrete or quantized, like tiny, indivisible units of existence. Perhaps the smooth continuum we experience is an emergent property at large scales, much like a smooth image emerges from millions of discrete pixels on a screen. In this picture, it becomes meaningless to talk about a distance smaller than a Planck length or a duration shorter than a Planck time, just as it's meaningless to talk about a location between two adjacent pixels. Whether spacetime is a probabilistic foam or a discrete lattice, the conclusion is similar. The familiar, continuous world we inhabit may be an illusion. It may be a macroscopic approximation of a much more unfamiliar, fundamental reality. At the Planck scale, the stage itself seems to melt away, leaving only a chaotic quantum fuzz where the rules of location, time, and causality no longer hold. These are some of the most profound and curious ideas in all of science. The thought that space and time might not be fundamental, that cause and effect could have a limit, challenges our deepest intuitions about the world. It is a curious thought, whether the Planck scale is a chaotic quantum foam, a realm of virtual black holes, or a place where causality itself dissolves. We'd be interested to hear your thoughts in the comments below. And if this kind of calm exploration into the world of physics helps you unwind, consider subscribing to the channel so you don't miss our future journeys into the quiet mysteries of the universe. The unreachable laboratory. The world described by Planck scale physics, the quantum foam, the breakdown of causality, the quantization of spacetime, is, for now, largely a theoretical landscape. The reason for this is simple and humbling. The energy required to probe this realm directly is astronomically beyond our reach. The Planck energy is roughly 10 to the power of 19 giga-electron volts, JV. The most powerful particle accelerator we have built, the Large Hadron Collider, can create collisions at energies of about 14 tera-electron volts, or 14,000 JV. This means the Planck energy is more than a quadrillion times higher than anything we can currently achieve. Building an accelerator that could reach the Planck energy with our current technology is not a practical possibility. By some estimates, it would need to be the size of our galaxy. It is, for all practical purposes, an impossible machine. This is the great challenge of quantum gravity. We have two beautiful and successful theories, and we know they must meet at the Planck scale, but the very place where they meet seems to be fundamentally inaccessible to direct experiment. We have found a kind of edge to our known physics, but it's an edge we cannot physically touch. This has led some to wonder if this area of physics is moving from science into pure speculation. If a theory makes predictions about a regime we can never test, is it still a scientific theory? This is a thoughtful question within the physics community. It is like having a map that shows a new continent, but that continent is on a star a million light-years away. We can describe what we think it might be like, but we cannot send a probe to confirm our theories. This is why physicists have had to become incredibly creative. If you cannot go to the mountain, you must find ways to make the mountain, in a sense, come to you. Direct observation is off the table, so the field has shifted its focus to a more subtle and ingenious approach, looking for indirect signs. The logic is this: if the Planck scale reality is a shifting, foamy chaos, then even if we cannot see the foam itself, perhaps its effects leave tiny, residual fingerprints on the reality we can observe. Like the faint tremors on the ground that signal a distant, unseen earthquake, perhaps there are subtle anomalies in our measurements that can only be explained by the strange physics of the Planck scale. The search for quantum gravity has become a patient search for these quiet echoes from the edge of reality. Glimmers in the dark. Faced with an experimental wall a quadrillion times higher than they can climb, physicists have turned to the cosmos itself as their laboratory. Fortunately, the universe is home to events far more energetic than anything we could create on Earth. One of the most promising ways to indirectly probe the Planck scale comes from studying gamma-ray bursts, GRBs. These are the most powerful explosions in the universe, sending streams of high-energy photons patiently across the cosmos for billions of years. According to some models of quantum gravity, the foamy nature of spacetime should affect how light travels. Photons of different energies might interact with the quantum foam differently, causing them to travel at very slightly different speeds. Over a short distance, this difference would be impossible to notice. But for photons that have traveled for billions of light-years from a distant GRB, this tiny discrepancy could add up to a measurable difference in their arrival time. If we detected high-energy photons from a burst arriving consistently later or earlier than low-energy photons, it could be the first real evidence of spacetime's quantum nature. So far, the results have been inconclusive, though they have allowed us to rule out some of the more extreme models. The search continues. Another ingenious approach involves looking for something called decoherence in matter waves here on Earth. Just as a particle can be in a superposition of states, large collections of atoms can be put into a quantum superposition of locations. These experiments are exquisitely sensitive to disturbances. The idea is that the constant jittering of spacetime at the Planck scale should subtly shake these delicate quantum states, causing them to lose their coherence faster than conventional physics would predict. Experiments are pushing the sensitivity of these devices to incredible levels, using a macroscopic instrument to listen for the faint, residual hum of the universe's quantum foam. The quest to understand the Planck scale is more than an abstract exercise. It is the final frontier in a centuries-long search for a unified theory of physics, a theory that could finally unite Einstein's gravity with quantum mechanics. Such a theory would help us approach some of the deepest questions we can ask. What happened in the first instant of the Big Bang? What lies at the heart of a black hole's singularity? Is spacetime fundamental, or is it an emergent property of something even deeper? Physics has indeed found an edge to our universe of understanding, a boundary where our current maps become useless. But this boundary is not an end. It is an invitation. It marks the beginning of a new kind of exploration, one that requires more ingenuity and patience than ever before. We are standing at the shore of a foaming, chaotic ocean, unable to dive in, but learning to read the messages in its faint and distant ripples. The answers are out there, hidden in the light from distant stars and in the quiet whispers of cold atoms, carrying faint echoes from the very bottom of reality. The end of reality's simplest rule. This, then that. A domino falls, then the next one follows. A glass slips, then it shatters on the floor. A switch flips, and a room floods with light. For all of human history, one rule has seemed absolute, inviolate, the bedrock of our reality. Cause always, always precedes effect. It's the most fundamental principle we know. It's the engine of logic, the foundation of science, the very arrow of time itself. Every action creates a reaction. Every beginning has an end that follows. We are born, we live, we die. In that order. This forward march is so deeply embedded in our experience that questioning it feels like questioning reality itself. It's the one thing we can count on, the simplest, most unbreakable rule. But what if this rule isn't a rule at all? What if, at the very fabric of existence, in the bewildering realm of the quantum, the universe doesn't care about our neat and tidy sequence of before and after? What if I told you that in laboratories, right now, physicists are creating situations where the causal order gets blurry, where A can cause B, and B can cause A, all at the same time? This isn't a thought experiment. This isn't science fiction. This is the frontier of physics, and it is forcing us to confront a profound truth. The simplest rule of reality doesn't just break. It transforms into something far stranger, more interconnected, and infinitely more mysterious than we ever dared to imagine. The unbreakable rule, our classical illusion. For millennia, the story of the universe was written in the language of causality. From the earliest humans who learned that striking flint against stone causes a spark, to the great Greek philosophers who formalized logic, our understanding was built on this simple chain of events. Aristotle, in his Metaphysics, laid out a framework of causes, all predicated on the idea that something must act to produce a result. The sculptor acts on the marble to create the statue. The action precedes the outcome. This intuition powered the scientific revolution. Isaac Newton's laws of motion are a symphony of cause and effect. An object stays at rest until a force acts on it. The universe, in the Newtonian view, was a grand, cosmic clockwork. If you could know the position and momentum of every particle at one moment, the grand cause, you could, in principle, predict the entire future of the universe, the grand effect. This idea, later known as determinism, painted a picture of reality as a perfectly predictable line of dominoes set in motion at the dawn of time. Even as our understanding grew, the core principle remained. The great philosopher David Hume cemented the idea of temporal precedence. A cause must occur before its effect. It seems self-evident, almost a given. How could an effect exist before the thing that caused it? It would be like a shadow appearing before the object casting it, or hearing an echo before you shout. This classical view requires a few basic things to hold true. First, as Hume insisted, is temporal order *. Cause happens before effect. Second, is local influence *. Causes and effects are connected by physical processes that travel through space. A thrown rock has to physically travel to the window to break it. There is no instantaneous, spooky, action at a distance. And third, asymmetry *. The flow is one way only. The rock breaks the window. The shattered window doesn't reassemble itself and send the rock flying back into your hand. This framework is not wrong. It is spectacularly right. It's the framework that lets us build bridges, send rockets to the moon, and predict the weather. It governs every single moment of our macroscopic lives. And for centuries, we had no reason to believe that reality operated any other way. We had constructed a beautiful, logical map of the universe. The only problem? The map wasn't the territory. And in the early 20th century, physicists peering into the infinitesimally small discovered that the territory was bizarre beyond all comprehension. They had stumbled upon the quantum realm, and in doing so, they found the first cracks in reality's simplest rule. The quantum twist, where causality begins to fray. The journey into the quantum world begins with light. For centuries, scientists debated its nature. Was it a particle, a tiny bullet of energy? Or was it a wave, an undulating disturbance? The famous double-slit experiment seemed to provide a definitive and, frankly, insane answer. It was both. When you fire single particles of light, photons, at a barrier with two slits in it, you don't get two simple bands on the screen behind it. Instead, you get an interference pattern, the classic signature of waves interfering with each other. It's as if each individual photon, traveling one by one, somehow passes through both slits simultaneously, behaving like a wave, and interferes with itself. This ability to exist in multiple states at once is called asterisk superposition. Before it's measured, the photon isn't in position A or position B. It's in a probabilistic cloud of A asterisk and asterisk B. The act of observing it forces it to choose a state. This was the first hint that at the quantum level, reality wasn't as solid as our classical intuition insisted. But superposition was just the appetizer. The main course, the concept that would truly challenge our understanding of cause and effect, was asterisk entanglement. Albert Einstein famously called it spooky action at a distance. Imagine you have two particles linked in a special way. Let's say they have a property called spin, which can be either up or down. If they're entangled, their fates are intertwined. No matter how far apart you separate them, across a room or across a continent, the moment you measure the spin of one particle, you instantly know the spin of the other. If one is up, the other is guaranteed to be down. This correlation is instantaneous. It appears to happen faster than the speed of light, seemingly violating the principle of locality. How can measuring particle A asterisk here instantaneously cause the state of particle B over there? Einstein argued this meant quantum mechanics must be incomplete, that there had to be some hidden variables that predetermined the spins from the start. For decades, this was a philosophical debate. Then, a physicist named John Stuart Bell devised a mathematical test, and the experiments were performed. The results were unequivocal. Quantum mechanics was right. There were no hidden variables. The correlations are real, non-local, and profoundly strange. Entanglement doesn't let you send a message faster than light, but it does show that the universe is connected in ways that defy a simple, local, cause and effect story. This was a prelude to the true revolution. Entanglement questioned the asterisk locality of causality. The next step was to question its very order. What if the sequence itself, the sacred, before and after, could be put into superposition? This brings us to one of the most head-spinning concepts in modern physics, the asterisk quantum switch. Imagine a photon on a journey towards two operations, gate A and gate B. Classically, it must pass through them in order. Either A then B, or B then A, but in the quantum world, we can use a property of the photon, like its polarization, to control its path. If it's horizontally polarized, it goes through A then B. If it's vertically polarized, it goes through B then A. Now, the quantum twist. What if we put the photon into A asterisk superposition asterisk of both horizontal and vertical polarization? According to quantum mechanics, the photon travels down both paths at once. In one branch of its reality, it experiences the causal order, A then B. In the other branch, it simultaneously experiences the causal order, B then A. It is A then B and B then A. When physicists in pioneering experiments at labs in places like the University of Vienna and the University of Queensland demonstrated this, it was a landmark achievement. By measuring the photon after it passed through this setup, they proved with statistical certainty that it had experienced a superposition of causal orders. The only way to explain the data was to accept that cause and effect themselves had been placed in a quantum superposition. Think about what this means. In one branch of reality, A influences B in the other. B influences A. Both directions of influence happen at the same time, within a single particle's journey. This is the point where our classical intuition completely shatters. The rule, cause precedes effect, is revealed to be the wrong question. The quantum switch shows that the universe doesn't always operate on a fixed timeline. It operates on a deeper logic where different causal histories can coexist and interfere with each other. The end of reality's simplest rule isn't an end at all. It's an awakening to a much stranger principle. The implications are staggering. Researchers showed that a quantum switch could let you pull a clear signal from two communication channels that are individually so noisy, they should scramble any message. By putting the channels in a superposition of orders, sending the message through A then B and B then A at the same time, some information gets through. It's as if indefinite causal order is a new kind of resource, a computational advantage that simply doesn't exist in our fixed-time world. And right here, at this dizzying point, it's worth taking a moment. We've journeyed from Newton's clockwork universe to a realm where time's arrow becomes a quantum superposition. Concepts like this don't just challenge our physics, they expand our entire perspective on reality. But truly grasping these ideas requires more than just listening. That's why I want to tell you about this video's sponsor, Brilliant.org. Brilliant is an interactive learning platform that makes understanding complex subjects in math, science, and computer science genuinely fun. Instead of just watching, Brilliant gets you to solve problems and build your intuition from the ground up. If the ideas of superposition and entanglement sparked your curiosity, Brilliant has entire courses on quantum mechanics that break these topics down into beautiful, bite-sized, interactive lessons. You can explore the double-slit experiment, get hands-on with the math of qubits, and see for yourself how the bizarre rules of the quantum world lead to these counterintuitive results. For me, the best way to learn is by doing, and that's Brilliant's entire philosophy. It helps you build a robust mental toolkit, not just memorize facts. So if you want to go deeper into the strange world we've been exploring, I highly recommend you check them out. The first 200 people to sign up using the link in the description below will get 20% off an annual premium subscription. By signing up, you're not just investing in your own knowledge, you're also directly supporting this channel. So, click the link, start your journey, and see just how far your curiosity can take you. The new reality, rebuilding the rules. So, if the quantum level is a tangled, superimposed mess, why does reality look so normal to us? Why don't we see glasses unshattering? If causal order is indefinite for a photon, why isn't it for a baseball? The answer lies in quantum decoherence. The strange quantum behaviors are incredibly fragile. They only survive in perfect isolation. The moment a quantum system interacts with its environment, even a single stray photon bouncing off it, the superposition collapses. The A then B, and B then A possibilities are forced to pick one or the other. A baseball is made of trillions of atoms, constantly interacting with air, light, and background radiation. It's being measured by its environment an incomprehensible number of times every nanosecond. This unavoidable interaction washes out all the quantum weirdness. The probabilities average out, the superpositions collapse, and what emerges is the solid, predictable, classical reality we know. So, classical causality isn't an illusion, It's an asterisk emergent property. It's what happens when you zoom out from the chaotic, probabilistic quantum foam. Just as the wetness of water emerges from H2O molecules, a single molecule isn't wet. The definite arrow of time emerges from a complex, interacting universe. The old rule isn't broken, it's the large-scale limit of much stranger laws. This has forced physicists to develop new mathematical languages that don't assume a fixed timeline. One is the asterisk process matrix formalism. It describes all the possible ways two labs, Alice's and Bob's, can be connected, without assuming any pre-existing causal order. It allows for Alice to signal Bob, Bob to signal Alice, or, crucially, for them to be in a quantum superposition of these possibilities. It's a way of doing physics where causality is an outcome, not an assumption. Now we venture into the most extreme environment imaginable, the intersection of quantum mechanics and gravity. This is the realm of asterisk quantum gravity asterisk, the search for a unified theory that we still don't have. Here, the very idea of causality faces its biggest challenge. In Einstein's theory of general relativity, gravity is the curvature of spacetime. This fabric also defines the causal structure of the universe. What can possibly influence what? But what happens if spacetime itself is a quantum object? Just as a particle can be in a superposition of locations, quantum gravity theories suggest spacetime could exist in a superposition of different shapes. This leads to a wild thought experiment, the asterisk gravitational quantum switch. Imagine a massive object in a superposition of two locations. Since mass warps spacetime, this means spacetime itself is now in a superposition of two different geometries. And if the geometry of spacetime is indefinite, the boundaries that separate cause from effect become fuzzy and superimposed. At this theoretical level, causality doesn't just get weird, it may dissolve into something more fundamental. This leads us to a highly speculative but tantalizing idea: retrocausality. Could effects, in some sense, ripple backward in time? This isn't about time travel. Instead, controversial, non-mainstream ideas like the asterisk transactional interpretation asterisk suggest that every quantum event is a handshake through time. When a particle is emitted, it sends out a wave forward in time, but also a wave backward in time. A potential absorber in the future sends a confirmation wave back. The transaction is only completed when this handshake between past and future is established. While it is far from a widely accepted theory, this retrocausal picture offers one way to explain some of quantum mechanics' bizarre features. From decoherence to quantum gravity, the message is clear. Our simple rule of A then B was never the whole story. We're discovering that causality isn't a rigid law handed down from on high. It is a dynamic, malleable, and perhaps even emergent feature of a reality that is fundamentally interconnected in ways that transcend our everyday experience of space and time. We began with a simple domino, a cause and an effect, a perfect, predictable chain. We end in a universe of superimposed histories and indefinite orders. We've journeyed to the edge of what we know and peered into what we don't. So, has the simplest rule of reality been shattered? No. It has been transformed. We've learned that the classical causality we experience every day is a robust, emergent feature of a complex world. But it is not fundamental. At the smallest scales, this deeper structure reveals itself. Causality becomes indefinite and non-local. It sheds its skin, moving from a simple relation between events in time to a feature of the underlying quantum processes that generate reality itself. This journey forces us to confront the biggest questions of all. Is causality a fundamental principle, or is it, like spacetime itself, an emergent property? The debate is fierce. Some physicists argue that a notion of causality is an inescapable theorem of quantum theory. Others suspect it's a useful approximation that completely breaks down at the Planck scale, the theoretical pixel size, of the universe, where our concepts of space and time may lose all meaning. This is the threshold where physics meets philosophy, leaving us with a profound sense of awe. We are like cartographers who spent centuries drawing the map of a single continent, only to discover it is but one island in a strange and wondrous ocean. The old maps are still useful for navigating the island, but they tell us nothing of the world beyond the shore. The end of reality's simplest rule is not an end to order. It's the beginning of a new understanding. The universe is not a simple clockwork machine, but a shimmering, probabilistic web of information. The next time you see a domino fall, remember what's happening underneath. Remember that the simple, certain, this, then that, is a beautiful and useful story we tell ourselves. But the true story of the universe is being written in a language we are only just beginning to decipher. A language where the distinction between cause and effect can dissolve into a single, unified, and beautiful mystery.